Good morning to the speakers, faculties, and all participants to fifth day of our FDP webinar. And today is the last day of our webinar. And for today, we have three sessions by three speakers. The first talk is by Professor Rukmani Mohanta Madam from University of Hyderabad. She will talk on neutrinos, the pathways to explore physics beyond the standard model. The second talk is by Professor Tanuja Mohanty Madam from JNU, New Delhi, and she'll talk on quantum effects and optical studies of nanostructures. And the third talk is by Professor Amresh Kumar Jaiswal sir from Niger, Bhubaneswar, and he will talk on quarks, gluons, and the quark-gluon plasma. And I request Prachi Madam, Dr. Prachi Mohanty Madam, to introduce the speaker to the audience. Prachi Madam, please.
Thank you, madam. Wishing you all a very good morning. We are delighted to welcome you to the last day of our ongoing webinar. It is a great pleasure to have our first speaker, Professor Rukmani Mohanta from University of Hyderabad. Professor Mohanta is an eminent physicist in the area of high energy physics. Her research expertise is traced between theoretical and experimental high energy physics. It primarily includes heavy flavor physics and CP violation, physics beyond the standard model, neutrino physics, and dark matter phenomenology. She has also been associated with long baseline neutrino experiments, NOVA and DUNE at Fermilab, USA. To her credit, she has published around 150 publications of international repute and has been awarded Indian Top Cited Author Award in the year 2019 by National Academy of Sciences, India. She has also been awarded with DST Ramana Fellowship, OWST Young Woman Scientist Award for Asia and Pacific region in the year 2011 by National Academy of Sciences, USA. So, without spending much time, I would request Professor Mohanta to enlighten us with her knowledge. Dear Madam, please.
Yeah, good morning to all of you. So let me begin by thanking the organizers for giving me this opportunity and also for the kind introduction. So I'm going to talk about neutrinos, the pathways to explore physics beyond the standard model. So the question arises, why should we choose neutrinos? Why they are so special? And what is so important about the neutrinos? So by the end of this talk or by the end of this 1 hour, I hope I will try to convince you that neutrinos are the most important objects and they are very elusive, as you will see, and they are very hard to detect, and that makes them very special. So the outline of my presentation, it goes as follows. So before directly coming to neutrinos, first I will introduce you to the world of subatomic particles, as there are many students in the audience. So I thought I will introduce first the subatomic particles, then give you some basic. Yes.
Your screen is not visible, not full screen. Please do it.
Oh, it's I am making this one as full screen, but it is.
It was visible clearly, but now it is not visible. Please.
Now?
No. It is visible, but make it full screen mode.
Okay, let me again then sign out and then.
Rakesh sir. Just help.
Yes. Enter screen. There. Is it visible now?
Yes. It's okay.
Okay. So the outline of my presentation, it goes as follows. First, I will introduce the world of subatomic particles. Then I will discuss the standard model of particle physics and its limitation. Then I will come to neutrinos. Then what are the interesting things about neutrinos, that like neutrino oscillation and the recent discoveries, and then finally I will conclude. So there are several unsolved problems of nature, and let us just try to see what are these unsolved problems. So we do not know exactly what principles govern energy, matter, space, and time at the most elementary level or most fundamental level. We still have not understood this one completely. And we also do not know what is the world made up of and how does it work. Although with the present accelerators or whatever be the length scale that we can probe with the present accelerators, we know the fundamental particles, but who knows these fundamental particles which are fundamental today, they may be composite tomorrow with the development of technologies. And then another point we do not have any idea is why there is no antimatter in the universe. Then we also do not know, like whatever we see around us, that is the visible sector, it constitutes only 5% of the universe. We do not have any idea about the rest 95%, which we named as dark matter and dark energy. So high energy physics or particle physics tries to answer these issues by collaborating with other fields and also to push back the frontiers of knowledge. And with these things, it also brings technological developments as an additional bonus point. So the next point is, why do we need why we need to study high energy physics? And there are three main reasons. From the basic knowledge, we know that the resolving power of a microscope, this is limited by the wavelength of light. Suppose we want to explore the structure of a object, of any object, then we have to use the microscope whose resolving power, it should be smaller than the size of the object. Otherwise, we can't study the structure of the object. Similarly, another idea or another thing that we can take into account is that the bats, they do their hunting at night. Obviously, they cannot see their prey and try to hunt them. What they use is basically they use sonar, that is sound navigation and ranging technique, in which they use high frequencies with wavelength which are comparable to the size of the insects. That is how by using sonar they can easily hunt their prey at night. So like bats, if we want to see small things, we need light with small wavelength or high frequency, because wavelength is inversely proportional to frequency. Hence high energy photons, since E is given by h nu. So if the frequency will be large, then we have to have high energy, and this high frequency, it basically related to small wavelength. That is, if we want to study any small structure, then we need to have very small wavelength or very high energy. Now, the second point is that from Einstein's mass energy relation, we know that E is related to mass by this relation, E equal to mc square. So this high energy, if E will be large, then M will be large. So high energy is equivalent to large mass. So with high energies, we can be able to produce very heavy particles. And the unit that we use in high energy physics is electron volt, which is the energy that a single electron it gains when it passes from a negative to positive terminal of 1 volt battery. Now, the third point is that from Boltzmann equation, we know that E equal to kBT or kT, where k is the Boltzmann constant. That means if the energy will be large, then the temperature will also be very high. So this high energy means high temperature. So with high energy, we can recreate the conditions at a very tiny scale, And this will give us information about what would have happened just after the Big Bang. So high energy physics teaches us about the early universe. That is, we know that our universe has been created from the Big Bang, and once the bang happened, then after that the universe expands, and we are now at this stage around 13.4 billion years after that Big Bang. So if we have high energy, then we can go back in time and we can understand what would have happened at the very early universe. This is another aspect of studying high energy physics. So the fundamental point or the main point in studying high energy physics is that we want to, or we try to understand what are the basic building blocks of nature and how do they interact with each other to form all the observable universe or the matter that we see in and around us. So we find that there are varieties of substances around us like stone, wood, mud, and water. Obviously, all these substances are not fundamental. So by fundamental, what we mean is that they do not have any substructure. That is, they will be point-like and they will not be made up of anything smaller. So once we know the basic constituents or these fundamental particles, then if we know their interactions or if we understand how do they interact with each other, then one can construct a myriad forms of matter. The ancient view was that all things are made up of these four fundamental objects: fire, air, water, and earth. And the atomic theory was taught by Acharya in India earlier than Democritus and Leucippus. However, these four fundamental objects, which were considered to be fundamental in the ancient time, are no longer found to be fundamental. So let us see how the development happened and where are we now and what are the fundamental objects. So let us come let us see that up to 19th century, the atomic theory was not completely established and matter was believed to be continuous. And at that time, the interactions that were known were electromagnetic and gravitational interaction. So the great German physicist Boltzmann, he committed suicide partly in despair in his colleagues that atomic theory was valid. However, shortly after this tragic incident, atomic theory was firmly established, and by the first quarter of 20th century, atom was found to be composed of electrons and nucleus. So once the matter is not continuous and atomic theory was postulated or established, it was found that the atom is composed of nucleus and electrons. And with this, the weak interaction was added to the list of forces. So we have three fundamental forces: electromagnetic, gravitational, and weak interaction. And the fundamental objects were nucleus and electrons. In the second quarter of 20th century, the nucleus was found to be again composed of neutrons and protons, and which since neutrons are neutral and protons are charged particles, then it is not possible to explain why the uncharged and charged particle, they should be confined to a small space or small region. That is why the strong force was introduced. So we have four fundamental forces. And in the third quarter of 20th century, the protons and neutrons, they were found to be again made up of still smaller entities, which are known as quarks. So this is the present day picture of atom. We have the nucleus. In the nucleus, the protons and neutrons are there. They are bound together inside this nucleus. And these protons and neutrons, they are again not fundamental. They are composed of still smaller entities or still smaller subjects, which are known as quarks. And the electrons, which are fundamental, they are moving around the nucleus. So if we take the size of the atom to be in some length scale of the order of 1, which is basically 10 to the power minus 10 meter, then the size of nucleus is of the order of 10 Fermi, which is 10 to the power minus 14 meter. Then inside this nucleus, proton is there, and proton size is of the order of 1 Fermi, which is 10 to the power minus 15 meter. And inside the protons, their quarks are there, and the size of quark is 10 to the power 18 meter. And electrons are also fundamental, like quark and electrons, they are fundamental. And till date, we can probe up to the length scale of 10 to the power 18 meter. That is why we call these quarks and leptons as fundamental. But if with improved technology, tomorrow these quarks and leptons, they may not found to be fundamental. They can still have some substructure. So at the present time, these particles, that is quarks and leptons, are called as fundamental particles or basic building blocks of nature. So now coming over to the energy scale that we require, or that is required to probe the length scale of 10 to the power 18 meter. Now let us see how we can relate this length scale to the energy. And we know that from the uncertainty principle, that is delta x times delta px is equal to of the order of h cross or Planck's constant, and delta p is related to energy. So this delta x is inversely proportional to energy. So if we want to probe small length scale, then we need high energy. So coming over to same atom, which is of the order of the size of say 1 angstrom or 10 to the power minus 10 meter that we have seen in the previous slide, we need energy of keV range, that is 10 to the power 3 electron volt. Then inside the atom, we have nucleus, which is of the order of 10 Fermi. We need the energy scale of MeV range or 10 to the power 6 electron volt. And for proton structure, which is 1 Fermi, we need energy scale of GeV, which is 10 to the power 9 electron volt. So as I mentioned, the basic building blocks of nature are quarks and leptons. And these particles, they are spin half particles. So they are fermions. They have to satisfy the Fermi-Dirac statistics. And unlike any observed particles in nature, this interesting point about the quarks is that they carry fractional charge. So far, we have not observed any fractional charge free particles in nature. So since the quarks, they carry fractional charge, they are not freely observable. We have 6 quarks and 6 leptons. And these 6 quarks, they can be arranged in 3 families or 3 generations. The first family quarks are known as up and down. Second family quarks, that is charm and strange, which are heavier than the first family quarks, and they are lighter than the third family quarks, top and bottom. So the charges of the top row of these quark generations, they have electric charge of plus 2/3 unit of electric charge, and the down, strange and bottom, they have electric charge of minus 1/3 in the unit of electron charge. Similarly, we have 3 generations of leptons. The electron, it belongs to the first generation of lepton, and there is a partner of this electron which is known as electron type neutrino. This electron type neutrino and electron, they form the first generation of lepton, and they are the lightest one. Similarly, the second generation of lepton, or the higher cousin of this electron, neutrino and electron, are muon neutrino and muon. They have identical properties, except that their masses are different. Similarly, the third generation of leptons are named as nu tau and tau. So these neutrinos, they have electric charge 0 unit, and electron, muon and tau, they have electric charge of minus 1 unit. So these 6 quarks and 6 leptons, they form the basic building blocks of our nature. And these particles, they interact with each other through these four fundamental forces. This is gravitational, electromagnetic, strong, and weak force. However, the gravitational force is very weak in comparison to or at this length scale. So basically, this gravitational force is neglected in the study of these subatomic particles. So we have only these three interactions, which is electromagnetic, strong, and weak interaction. Then these interactions, they are not contact type of interaction. These particles, they can interact through the exchange of some mediating particles, and these particles are known as force carriers. And for electromagnetic interaction, the force carrier is photon, a single photon is there. For strong interaction, the force carriers are gluons, and there are 8 gluons. And for weak interaction, the force carriers are known as G boson and W boson. There are 2 charged W boson and 1 neutral Z boson. And these particles are basically we need to have some theory. The theory is known as Standard Model, which describes the interaction of these particles, of these elementary particles. However, in the Standard Model, these particles are massless, but we know that they are massive. So the mass term generated by this Higgs boson. So this is the importance of this Higgs particle. So these are the fundamental forces: strong, electromagnetic, weak, and gravitational. And these particles, they interact with each other through the exchange of these forces. So this is the summary of the different types of forces, their strength. And again, another important point to be noted is that the range of the forces, they depend on, or they inversely proportional to the mass of the mediating particle, since the mediating particle of electromagnetic interaction is photon, which is massless, therefore its range is infinite. And with all the charged particles, they experience the they interact through electromagnetic interaction. Although the gluons, which are the mediating particles of strong interaction, they are also massless, but the strong interaction range is very short because of their special feature. Like unlike the photons, the gluons, they are charged under these strong interactions. And all the quarks and gluons, they experience strong interaction. The weak interaction is very short range because the mediating particles, W and Z bosons, they are very massive. And all quarks and leptons, they experience this weak interaction. Now let us have the quick glance of the Standard Model. This Standard Model is very successful theory, and it describes our universe at the most fundamental level. It's an elegant and very triumphant model describing the elementary particles and their interactions. All these particles, they are experimentally observed, except this Higgs boson, which was not discovered till 2012. So there was some speculation that the Standard Model might be not correct. However, this Higgs boson, it was discovered in LHC experiment in 2012. So Standard Model is complete now. But although all the particles are observed and we understood more or less the behavior of all these particles, but there are certain issues which are still open issues, and for which Standard Model, it doesn't provide any satisfactory explanation. So what are these what are the limitations of the Standard Model? We know that our universe was created from Big Bang, and now we are left with only the matter particle. So what happens if the universe is created from Big Bang? Then we should expect that there should be equal amount of antimatter. However, whatever we are seeing around us, all are composed of matter particles, and what had happened to antimatter, that one we do not understand. It also doesn't provide any explanation for the dark matter content of the universe. And as I will discuss later, now we know that the neutrinos are having some non-zero masses, but Standard Model, it predicts only zero neutrino mass, or in the Standard Model, neutrinos are massless. So how we can accommodate the non-zero neutrino mass? So it is very obvious that Standard Model, it has to be extended. So the question is, what is the underlying fundamental theory, And can we get any information from the neutrino sector? Now let us come to neutrinos. And neutrinos, they constitute only 1/4 of the matter particle, and they come in 3 flavors, that is electron type neutrino, muon type neutrino, and tau type neutrino. Since they are neutral, electrically neutral, their charge is 0. They interact only through weak forces because they are massless. They cannot interact through gravitational interaction. They are chargeless. They cannot interact through electromagnetic interaction. And they are leptons, so they cannot interact through strong interaction. So they can interact only through weak force. They are assumed to be exactly massless in the standard model. Although they make up only 1/4 of the elementary particles of nature, they basically they are overabundant, and they are the second most abundant particles in the universe with 330 neutrinos per centimeter cube. So a trillion of neutrinos are passing through us in each second. However, they interact so weakly that we cannot detect them. That is, their cross section with, if we consider the cross section of a neutrino with a proton, then the cross section, it is found to be like 10 to the power minus of 44 centimeters square. And this much of cross section, it requires the mean free path of neutrinos to be of the order of say 50 light years. That is, if you have one neutrino, it can travel 50 light years before interacting with any matter particle. Now let us come to the point that why are neutrinos interesting? From the cosmological point of view, they played an important role during Big Bang. They could explain the matter-antimatter asymmetry of the universe. They are the most abundant form of the matter in the universe. The most abundant particle is photon, that is the force carrier. However, the neutrinos, which are the second most abundant particle form of matter in the universe. From the astrophysical point of view, they govern the life and death of stars. And from particle physics point of view, they are a window on physics beyond the standard model. Presently, they represent the only experimental hint in that direction in particle physics. Unfortunately, the neutrinos are quite difficult to detect as their mean free path is of the order of light years. So this requires that we have to have if we want to study the properties of neutrinos, then we have to have very intense beam. We have to have very innovative ideas to detect the neutrinos, and also sources. Like we have to have very intense source of neutrinos. So from where we'll get neutrinos? Neutrinos are omnipresent. We will find many sources of neutrinos. For example, if you consider sun, it gives 65 billion per centimeter square per second, and the energy of these neutrinos of the order of MeV. We can found neutrinos from supernova explosion, from geoneutrinos, from nuclear reactors, from Big Bang. We are having these relic neutrinos of 330 per centimeter cube. We can have from human body extragalactic neutrinos and so on. And also we will get from particle accelerators. So we can have neutrinos from various sources with varied energy ranges. So what are the unique features of neutrinos? They are the second most abundant particles in the universe. They are the lightest massive particles, 1,000,000 times lighter than the electron. So far, no direct mass measurement is done yet. They are the most weakly interacting particles. They travel in a straight line, and they can bring information from deep within the star, not possible even with light. They are invisible because they do not have the electromagnetic interaction, or they do not interact with light. To stop neutrinos with a lead shielding, we need or the mean free path is of the order of light years. For electromagnetic radiation like alpha, beta, or gamma radiation, if we want to stop these radiations with lead shielding, the mean free path is 50 centimeter, whereas if we want to stop the neutrinos from sun or of the MEB range neutrinos, it depends on the energy. The stop this mean free length, it should be light years. That is why it is very difficult to stop neutrinos. Now let us come to the beginning of neutrino era in 1932. So there was an issue in the beta decay experiment in 1932. That is, if you consider the beta decay process of X nucleus decaying to Y nucleus plus electron, then if we consider the energy momentum conservation, then the energy of electron, it should be given by the mass difference between, or the energy difference between this parent and daughter nucleus. That is, the energy of electron, emitted electron, it should be fixed, which will be given by the difference between the energy of this parent and daughter nucleus. However, experimentally it is found that these electrons, they are not having a constant energy, but they are having a varied energy spectrum. Some of the electrons, they are having this much of energy, and some of the electrons, they are having zero amount of energy. So this observation is very unexpected. That means energy momentum relation or energy momentum conservation relation is in danger, because if some of the electrons, they are having say continuous energy spectrum, then this energy momentum conservation relation is invalid. So Pauli, he didn't believe in energy momentum violation. So as a desperate remedy, what he proposed is that in addition to this electron, there should be another particle which is emitted during this beta decay process. And since this particle is very rarely interacting or very weakly interacting, it is escaping the detector and it is not leaving any trace in the detector. That is why it is, whatever be the balance amount of energy in this process, it is carrying away that rest energy. So this invisible particle he named as neutron, and later after the discovery of neutron, it was renamed as neutrino, which means that, or its meaning is the little neutral. It is very feebly interacting. It is very hard to detect. So for stopping neutrinos from sun with lead shielding, we need light years of path length. Let us come to the discoveries of neutrinos. As I mentioned, there are 3 different types of neutrinos. So how can, since these neutrinos are electrically neutral and they are also massless, so how can we differentiate between, or how can we confirm that there are 3 different kind of neutrinos? So this electron neutrino was discovered in 1956, for which this Reines and Cowan, they got the Nobel Prize in 1995. So this neutrino is discovered from this reaction, that is electron type antineutrino. When it interacts with proton, it produces the neutron plus a positron, and this positron is, since this is a charged particle, we can detect it this one. So for this process, always we observe this positron. We never observe any muon or tau type, which implies that this one, it has the characteristic that it is electron type neutrino. Similarly, the muon neutrino, it was discovered in 1962, for which these 3 gentlemen, they got the Nobel Prize in 1988, and they used this decay process, that is pion decaying to muon plus nu mu bar, and this nu mu bar, they interact with the detector material N, and it produces this N prime. This is the nucleus plus mu minus. That is, in this case also, we are always observing the muon, never we observe any electron or tau. This means that whatever be this neutrino, this one is having different properties, like different properties than this electron type neutrino and tau type neutrino. That is how we can differentiate with their accompanying charged leptons, that there are 3 different types of neutrinos. Similarly, the tau neutrinos, it was discovered in 2000 at formula. So we have 3 different types of neutrinos, and all these 3 different types of neutrinos are experimentally observed. Now let us come to the properties of neutrinos. the sun, we get the energy from sun from this reaction. That is four hydrogen atoms give us helium, and then they produce 2 neutrinos and light. So sun it gives intense beam of neutrino flux, and there is one model which is known as standard solar model that gives us the prediction for the number of neutrinos that we can get from sun. So then in the detector on the earth, we can try to measure the electron type neutrinos coming from sun. So what it is found is there are various processes in which neutrinos can be produced in sun. This is one process. There are also proton-proton chain. There are also beryllium chain, and so many processes, 6-7 processes, and all these processes they have this. They produce these electron type neutrinos with MeV range. So from standard solar model, we can get the idea about the electron type neutrino flux, which are produced in sun and coming to earth. And in the detector on earth, it is found that the number of neutrinos, the neutrino flux is found to be half of their theoretical prediction. The yellow band, it represents the theoretical prediction, whereas this bar, it represents the experimental measurement. So in most of the cases, or in all the cases, it is found that the experimental result is half of the theoretical prediction. So this implies that there are 3 possible solutions, and these experiments are done not only single experiment, there are several experiments, they observe the same result. So the possible solutions could be all experiments are wrong. This is highly unlikely as different experiments use different detection techniques. Then the second possibility could be the standard solar model prediction is wrong for the neutrino flux. This could be possible as sun is extremely complex system and there could be some theoretical error. Then the third possible solution could be neutrinos can oscillate from one flavor to another during their journey from sun to earth. This one is interesting one. So that since some of the neutrinos, they are oscillating to another flavor, and the detectors on earth, they are tuned to detect only the electron type neutrino. This implies that since some of the electron type neutrinos, they are oscillating to muon type neutrinos, that is why they are detecting only half of the solar neutrinos on earth. So this is an interesting solution. Now let us come to the another issue which was known as atmospheric neutrino puzzle. This one was 1980 to 1998. So we know that our atmosphere is always bombarded with high energy cosmic rays from outside. So when these cosmic rays, they hit the protons or the air molecule on the atmosphere, they produce pions, charged pions. These charged pions, they decay to this process, mu plus nu mu. This muon again decay in this way. So the interesting point or the important point to be noted here is that we get 2 muon type neutrinos and 1 electron type neutrino. Similarly, from pi minus, we can get similar 2 muon type neutrinos and 1 electron type neutrino. So here we are not distinguishing between neutrino and antineutrino. So if we measure the total combination of muon plus anti-muon neutrinos and take the ratio with the corresponding electron and electron antineutrino, this ratio is expected to be 2. However, experimentally what is found is that this ratio is not found to be 2, it is found to be 1. So let us see the experimental data. Sorry. And so if we consider the number of electrons, that is electron neutrino, these are the data points and these are the theoretical prediction. There is no mismatch between the electron type neutrino. Whereas for muon type neutrinos, this is the detector. Some neutrinos are coming from top of the earth, this side, they are traveling only the 15 kilometer, and some neutrinos are coming on from the other side of the Earth. So they are traveling 13,000 kilometers. So the neutrinos which are coming from the bottom of the Earth, this one is expected, but the experimental data is like this. And for the neutrinos which are coming above the Earth, they are matching with the theoretical and experimental observation. They are in agreement with each other. This implies that the neutrinos which are coming below the Earth, they are oscillating to another type of neutrinos. That is why we are not detecting them, and there is a depletion in their data. So this implies another solution for the atmospheric neutrino puzzle, that is nu mu is transforming to nu tau, and there will be some oscillation. So what is neutrino oscillation? Let us come to the neutrino oscillation. So this is a quantum mechanical phenomena. We have the electron and muon type neutrinos. These are, let us take for simplicity first only the two flavor case. So this electron and muon type neutrinos, they are known as the flavor eigenstate, and they can be linear combination of their mass eigenstate, which are defined as nu1 and nu2. So we can write the electron type neutrino as a combination of nu1 and nu2 with this mixing angle theta. So we can write nu e nu mu equal to sine theta, this mixing matrix, which is a orthogonal transformation nu1 nu2. So we can write similarly nu mu as a linear combination of nu1 and nu2. So let us now consider the case that if we have this nu mu state at time t0, what will be the state at nu mu at time tu? So we have to consider the time evolution of nu1, which is e minus I e1 t nu1, and for this one e minus of I e2 t nu2. And then after a little algebra, like we can use the relativistic energy momentum relation, and after the expansion we can get the transition probability that if we are starting with a muon type neutrino at time t0 and we are detecting an electron type neutrino after time t, then this is given by these expressions. It depends on sine square 2 theta, the theta is the mixing angle, and it depends also again the mass square difference and this length traveled by the neutrinos and energy. So this is known as appearance experiment or appearance probability, because we are getting electron type neutrino starting from a muon type neutrino. Similarly, the disappearance experiments, that is known as nu mu to nu mu, that is how many muon type neutrinos they are disappear during this transition, which is 1 minus of this one. So let us come to the two flavor case. This is the appearance probability, and this is the disappearance probability, and it depends on the mass square difference, that is m2 square minus of m1 square. So since this oscillation it happens in nature, this implies that the neutrinos are not massless as predicted by standard model, but they have to have some non-zero finite mass. So this is the typical example of for a specific value of mixing angle theta and for specific energy range and for specific value of delta m square. If we start with say electron type neutrino, after certain, here we are having only pure electron type neutrino, so this value is 1. As we go with time, then some of the electron type neutrinos, they will transform to muon type neutrinos, so this probability will reduce, and again this muon type neutrinos, they will go back to the original electron type neutrino, and this is how neutrino oscillation happens, or they change their flavor during the propagation from source to detector. So what are the interesting parameters? So as we have seen, the transition probability or the oscillation probability from one flavor to another flavor, it depends on the mixing angle theta, it depends on the mass square difference and the length of the transition as well as energy. So this mixing angle, it defines how the mass states are related to the flavor eigenstate, and this mass square difference it is related to the mass difference between, or mass square difference between the two mass eigenstate, and L by E, it gives the ratio of the baseline length or the source to detector length by energy. Now, since we have 3 flavor neutrinos, we cannot stick to 2 flavor neutrinos, so we have to just extend the idea of 2 flavor neutrinos to 3 flavor neutrinos. So these flavor eigenstates, they are related to the mass eigenstate by this unitary matrix, and this unitary matrix is known as PMNS matrix, that is Ponte-Carbo, Mackie, Nakagawa, and Sakata. So a 3 by 3 matrix, unitary matrix, we can parameterize by n times n minus 1 by 2 real parameters and n minus 1 times n minus 2 of physical phases. Therefore, this matrix, it can be parameterized by 3 mixing angles and 1 phase. So this is how we can represent, or we can write this mixing angle. The 3 mixing angles will be similar to the OLR mixing angles in classical mechanics. There will be rotation in 2-3 plane, 1-3 plane, and 1-2 plane. And the phase is associated with the rotation matrix in 1-3 phase. The information about the mixing angle 2-3, it comes from the atmospheric experiment. This information about the 1-3, it comes from the reactor experiment, and 1-2, it comes from the solar experiment. So in the oscillation, transition oscillation probability, it depends on since there are 3 flavors, there will be 2 mass square difference, and we can write these 2 mass square difference as delta M21 square and delta M32 square. And there will be 3 mixing angles, theta 12, theta 23, theta 13. This one is known as solar mixing angle, theta 23 is atmospheric mixing angle, and theta 13 is reactor mixing angle, and there will be 1 phase. So what is the essential ingredients for neutrino oscillation? That is, they have to be massive. Okay, so for this neutrino oscillation, observation of neutrino oscillation, these 2 gentlemen, they got the Nobel Prize in 2015. They are Takaki Kajita from Super Kamiokande experiment, Japan, and A.B. McDonald, he is from SNO experiment at Canada. So as the probability, it depends on 2 mass square difference and 3 mixing angles. So the main objective of the neutrino oscillation experiments is to measure precisely these parameters. So far we know the values of these mixing angles, theta 12, theta 23, and theta 13, and we know the value of this delta M21 square, both its magnitude as well as sign, which is known as the solar mass square difference. However, we know the magnitude of delta M square 32, but we do not know its sign. That means there is a possibility that this M3 is greater than M2. So in that case, your M1 square, M2 square, and M3 square, they will have this structure. M3 square is greater than M2 square. So this one is known as normal hierarchy or normal ordering. And the other case is if when this one will be negative, then M3 square will less than M2 square. And this one is known as inverted hierarchy. Similarly, we determine the value of sine square theta 23. So this implies that whether theta 23 is greater than pi by 4 or theta 23 is less than pi by 4. This is also not known yet. If theta 23 is greater than pi by 4, this one is known as higher octane, and if theta 23 is less than pi by 4, this is known as lower octane. So the precise determination of these oscillation parameters is one of the foremost goal of the present and future oscillation experiments. Okay, so there are many open questions still now. So these mass square differences here, if you note that one, this delta M21 square is of the order of 10 to the power minus 5 PeV square, and delta 31 or 32 square is less of the order of 10 to the power minus 3 EV square. Whereas if you come to the electron mass is 0.5 MeV. So the neutrino masses are sub-EV range. So we do not know the mechanism why neutrino masses are small. And we measure only the mass square differences, and we do not know the exact mass scale of these neutrinos. So what is the mass of neutrinos? Then we also do not know whether they obey normal or inverted hierarchy. Then that CP symmetry is violated in neutrino sector or not. Are there any other light sterile neutrinos? These are many of the open questions. So if we can understand these, if we can find some answers to these questions, then this will lead to physics beyond the standard model. Now, okay, so I'll just skip these things. Now these neutrinos, they can also explain us the origin of our universe. So as we know, our universe was created 13.7 billion years ago. When the universe was created, there was no matter, only we have the Big Bang. And as the universe, it expands and it cools down, the matter was able to form through this reaction. Photon plus photon or energy plus energy will give us particle and antiparticle. So this naive formulation of Big Bang, it implies that there should be matter and antimatter symmetric universe. However, the present universe is composed of only visible matter. So what the question is, what happened to antimatter? So the number, since there is no antimatter, the number of baryons is not equal to number of antibaryons. So if we find out the baryon asymmetry of the universe, that is this parameter is eta, which is the difference between number of baryons to number of antibaryons to number of photon, because this number of baryons plus antibaryon, that will be equal to 2 times number of photon. This value is found to be 10 to the power minus 10 from Big Bang nuclear synthesis. However, now let us come to, or let us try to understand how we can generate this baryon asymmetry of the new universe. So this baryon asymmetry of the universe can be generated dynamically rather than being an initial condition. So if we consider that if it would be some initial condition, then it would have been highly tuned. That is, we need 10 to the power 10 antimatter particle and 10 to the power this only one extra antimatter particle. So there will be huge fine tuning. So this only one remaining matter particle, this should create, it should create the universe. That means it is very highly fine-tuned theory. So to explain the baryon asymmetry of the universe in 1967, Sakharov proposed that this surplus matter is possible only if these 3 conditions to be satisfied, that is baryon number violation during the evolution of the universe, CP should also be violated, and departure from thermal equilibrium. Since CP violation is there in the neutrino sector, if we can understand CP violation, then it can also explain us the origin of the universe. So I will just discuss a little bit about CP symmetry and then I will stop. So since nature doesn't know whether we observe directly, parity means mirror image, and the nature, it doesn't know whether we observe it directly or through mirror image. This parity violation, it tells us that nature, it makes a difference between left and right, but which one is what, it doesn't fix us. Like if you take the convention, we are taking our left like this. If we take our convention like right hand is left and transform everything, then there is no difference between left and right. Similar argument can also apply for the electric charge. So under parity, left transforms to right, and under charge conjugation, a particle, it goes to antiparticle. So this CP is the combined operation of this charge conjugation and parity. And initially, it is believed that all the interactions, they are invariant under this combined operation of charge conjugation and parity violation, parity inversion. However, later it is found that the weak interaction, that it doesn't respect this CP symmetry or CP violated in weak interaction. And since neutrinos are there or neutrinos, they interact only, or they experience only weak interaction. So there, it is expected that neutrinos, they also violate CP, and the CP violation in the lepton sector, it could be a possible reason to explain the matter-antimatter universe, asymmetry of the universe. So let us now, there are many experiments which are going worldwide to understand the properties of neutrinos, and in India also, we have this India-based neutrino observatory. So this lab is expected to come out in Tamil Nadu, and this lab, it uses the 15 kiloton magnetized iron calorimeter, and the main objective of this INO project is to solve the mass hierarchy problem. So to conclude, neutrinos are a fascinating and critical component of Standard Model. They have managed to surprise the particle physics community repeatedly over the past 75 years. There are many experiments going on worldwide to understand the properties of this tiny and mysterious particle, which will tell us more about the universe. And we need to build new experiments to reveal new discoveries. So once we are trying to build new experiments, we need to have to advance our technology of creating intense neutrino sources and detecting neutrinos, and hopefully neutrinos will continue to spark the imagination of all. Okay, I'll stop here since my time is over. So if you have any questions, then I will be happy to take.
Thank you, Professor Mahanta. It was indeed an insightful presentation. The slides you saw gave us a close look at the unique features of the neutrinos. Moreover, the significance of neutrino oscillation as a gateway to explore physics beyond Standard Model. So after this informative session, we can take questions from the audience. So here is the first question. Does
Yes.
there exist any justification for grand unified theory from the neutrino model?
Yes, definitely. Because in the Standard Model, the neutrinos are exactly massless. So you need to have some beyond the Standard Model scenarios to explain the mass generation, for which you have to consider, like I had the slide, but I could not show. You have to consider like right-handed neutrinos or scalar triplet or something. So once you consider these new particles, they will give you, or it will give you the model beyond the Standard Model, and this new extended model, it will lead to grand unified theories. Ultimately, our objective is to take the bottom-up approach and reach the grand unified theories.
Thank you. The next question is, can quarks be converted to energy?
Quarks, because we do not observe free quarks, so freely you cannot convert the quarks to energy, but the reverse is not true. You can create the quarks from energy. The reverse is not true. You cannot use quarks as you cannot accelerate the quarks and create energy. So all our accelerators, they use the stable particles like electron, proton, antiproton. You can create the antiparticles and then collide them and create the energy. However, since quarks are not freely observable, you cannot use them directly to create energy. Accelerate them and create the energy.
Thank you. The next question is it possible to have charge lepton flavor violation?
Yes, definitely. There are many experiments, they are looking for charge lepton flavor violation, but so far we have not observed any conclusive evidence. We are having only the upper limit. For example, muon to E gamma. We have only the upper limit, 10 to the power minus 13. The probability of muon transforming to electron plus photon, the probability is 10 to the power minus 13. So there is charge, and also muon G minus. So there, people are, or many experiments, they are looking for charge lepton flavor violation.
Okay. The next question is, do neutrinos are fundamental particles, or there are any evidence that they consist of sub-sized particles?
As I mentioned, till now, we have reached up to the fundamental length scale of 10 to the power minus 18 meter, and at this length scale, neutrinos are fundamental. Tomorrow, it may so happen that it is found to be that they are composite particles.
To continuation with the previous question, is charge lepton flavor violation possible? It is a question, what about tau to 3 muons?
Yes. Tau to 3 muon, then muon to E conversion inside the nucleus. All these are possible, and for all these processes, we have only the upper limit of the order of 10 to the power, the branching fraction or the probability that such transitions can occur. This probability will be 10 to the power minus 12 to 10 to the power minus 13.
That's all for the question and answer session. Thank you, Professor Mohanta, for your attention and response to the questions. Now, on behalf of Department of Physics, I would like to extend my thanks to Professor Mohanta for her valuable contribution.
Thank you very much.
Thank you, madam. Rukmini madam, thank you for the night.
Thank you. See you sometime.
Yes, madam.
Okay, bye.
Bye. So next session.
Okay. Right. So let me just do it. This. I can just minimize here. Right. अभी पहले
So welcome all of you to the next session. So now I invite Professor Tanuja Mohanty Madam to our webinar. Tanuja Mohanty Madam from JNU, New Delhi, and she will be talking on quantum effects and optical studies of nanostructure. And to give a brief introduction about Tanuja Madam, I request Deepika Madam to continue.
Thank you, ma'am. Okay, so good afternoon, all. Next, we'll move for our next talk. So, I will heartily welcome to Professor Tanuja Mohanty, Professor at JNU Delhi from 2006 onwards, and she has received her PhD from Utkal University in 1999. She has pursued postdoc from 2004 to 2006 at Inter-University Accelerator Center, New Delhi. She is honored with SBI Award for State Topper in 1985, CSI Research Associate Award in 2000, DST Fast Track Young Scientist Project in 2004, DST DAAD Research Project in 2011, And her areas of interest are experimental condensed matter physics, which includes nanoscale semiconductor and metals, graphene and graphene-based nanocomposites, ion interactions with solids. She has also collaboration in physics department, Duisburg University, Germany. She has best paper reviewed publication in Journal of Physics Chemistry, Applied Physics Letter, Journal of Nanoscience. She has also recent peer-reviewed journals in Applied Physics Letter, Journal of Physical Chemistry, and Journal of Material Science. Her title of today's talk is Quantum Effects and Optical Studies of Nanostructures. With this short biography, once again I am glad to greet Professor Tanuja Mohanty Madam to present her talk before us. I request Madam to please proceed here and share her screen. Yeah. Thank you, ma'am.
Okay, thank you, Mr. Babita and Mr. Sapya. So thank you for the nice introduction. I think the title of the talk something different, a little bit different. So which I sent. So let me just start it. At the outset, let me thank the organizer, particularly the HOD of Physics Department, Dr. Babita Madam, for inviting me to give a presentation. Just let me just increase the voice. So I will be talking on just 1 minute. So as it's in the invitation or in the list, it is written. It is for the audience is from MSc students to the teachers. So my talk will be covering up like different aspects, starting from the students to make it interesting if I can, and then I'll follow up some of the research work, which is so I actually the title was like this, which is same as whatever you have told. So the defect-induced optoelectronic modification in graphene-like 2D materials, and this is like our JNU and
sorry, madam.
Yeah.
Is it possible to make it full screen?
I have made it full screen.
And
Not possible.
actually,
It is not.
there is. Yeah, yes, that is same, but it's not full screen.
No, from here, just 1 minute. I have made it that again. I am trying it to make it from this side because
Yes.
Okay. So now it is done. Can
No,
you see?
actually, you can share your full entire screen so that it will be visible to us full screen.
Share my entire screen. Where it is? Slides. So even if I start beginning, this also.
No, madam. Actually, you can stop your share first.
Stop my share.
Go to the browser, madam.
Okay. So stop sharing. Then
Yes.
tell
Okay.
me.
Then again, yes, share your entire screen.
Yeah, entire screen.
Okay. Then go to your PPT.
PPT, right? I had gone like this, and then
Full screen.
then allow, but it came. So I should made it before. I think
Okay. Now I make it full screen.
Just 1 minute. Is it coming now?
No, madam.
Oh, just 1 minute. Stop sharing. If I
Then
make okay, just before coming, if I make the presentation, but how will go there?
madam, there is a sharing option. There is a 3 option. One is your entire screen, a window, a tab. You have to share your entire screen.
Actually, I had done it the entire screen, or I will send the PDF of this one. Present now your entire screen. I am doing it that entire screen actually.
Yes, madam.
Then select the window or screen. Okay. So then it comes this CT presentation. Okay, the entire screen. Now, if it is the entire screen, it is coming the screen like okay. So allow. And if I make the presentation here,
Now okay. Now okay. Yes, madam.
Sorry for
Thank you, madam.
the 5 minutes point. Okay, so let me just start, and I'll stick to try my best to stick to the time, even if 5 minutes have gone. So the title of my talk is Defect-Induced Optical Electronic Modification in Graphene-like 2D Materials. And here is our department in School of Physical Science, and this is the JNU and School of Physical Science here. At the outset, let me thank Dr. Kaddi Kanjilal, IUC New Delhi, because in most of the work he is involved. And then the ISRO Respond project for the finance. And some of the students' work who had actually already been graduated, they are some of part of their work which I will be presenting to us once, and some of the students who are working. Now, outline of my talk will be the introduction to the defect materials. As I said, the defect induced, so I will just focus on the defects and the why 2D materials. Then we'll go to the defects which can be generated by swift heavy-ion irradiation and the modification of some optical and surface electronic properties. And then we'll wind up it with the conclusion. So start with, as you said, that you have those students also. So let me start with the defects in a material. So in a material, there can be different types of defects. One can be a point defects, line defects, planar defects. So point defect, which is normally is studied to us, to all MSc students, that is Schottky and the Frenkel defects. But besides that, there are other types of defects, which are line defects and planar defects. Line defects are in a linear type, and planar defects in a two-dimensional. Line defects is one-dimensional, and other defects is the stacking fault, and the volume defect is also there. So these defects, why they are very important? Because they have the influence on the properties of the material. So properties of the material, they has a major influence. So that can be changes because of the defect interaction, and defect interaction, they play a major role for the properties of the materials. Now, so the pictorial wise, we have the like point defects, like normally when you say it is in a crystalline or an amorphous, you know that it is not a periodic ordering in the ordering in the sample position lattice. So it is not there. If there is a disturbance, then if somebody has gone out, then it is a point defect here. So we call it as a regular vacancy, which the atom has gone out of the lattice site, and here interstitial, it has gone from some site and has occupied a space in somewhere between. And that gives you a Schottky defect here. These are the Schottky defects, and this in between, that you get it at the Frenkel defect, like this type. So Schottky defects and Frenkel defects are taught to even to the MSc students from the beginning, and it is found mostly in the ionic crystals. So this type of defects is easier to produce, and that is like a single vacancy. If you say one is removed, then it is a single vacancy. And if some interstitial, that means it is not in a regular position, but in between the lattice position it is there, then it is called those interstitial defects. Now, what are the other types of defects? That is the line defects. So line defect means, we say it is a line defect, means those defects that they occur in a line, means not only in a single isolated place, but that irregularities occur throughout the line. So ideally, if had it been a regular crystal, it should have gone straight line. But you see that is the difference again changes. So we say it as a line defect. And that means the line defects are the irregularities or deviation from the ideal arrangement. Also, they are called as the dislocation. And these dislocations affects the mechanical and other properties. So always, when we heard about the word that is defect always doesn't mean it is a bad, but it has some positive effect, and a very good positive effect, which we will see later on. So this is the line defects, and we use the terminology that is a Burger vector. So Burger vector means you are going in a particular line like this, but because of the irregularities, you will not, from the starting point with particular, you will not come to the same point again. You will just go ahead of it. So that is the point that connects the failure of the start and the end points as a result of introduction of some half plane atoms. So here this distance and here this distance, that total surrounding that differs. So that difference is called the Burger factor. So that is used. So this type of things we say it as an edge dislocation, because this dislocation occurs that because of the extra row of atoms has been introduced into the crystal. And there is a screw dislocation. Screw dislocation means that is a dislocation that is like you have a plane of which one is above the other, and that type of dislocation is you have a slip plane. So means they are not at equal height. Here you can say it is like slanting mode, and there is a straighter difference. So this is like a screw type, because screw when goes, it is, you will see never it is in a planar position. So now you know that what is one is the line defect and another is the point defect, and both the defects they can also just 1 minute. Let me just, if I can just remove this one, just 1 minute. Okay, one side. So these vacancies which are there, they also can interact with the dislocation. So you have a line defect, they can also, there is a, so the dislocation tends to attract the vacancies and relieve the compressive stress. So they are called like a dislocation climb. So this type of deformation can also, but because it can be a combination of vacancy as well as the dislocation. So here you can have the dislocation as well as some interstitial. So that can be a combination of that, so which is called the dislocation climb. Oh, it is not going. Just 1 minute. Okay, sorry. Why it is not? Oh. Just 1 minute. Yeah. So, am I, this was visible or not?
Yes, madam.
Okay. Now, these impurities, that also, they can also interact with the dislocations. So, dislocations, those dislocations means you are saying that impurity here it is there and there is the dislocation. So, not only can be the point defects can be there can be a combination of both point defects as well as the line defects. So, different types of arrangements which we can see here. So, this type of arrangements are like, so you have these arrangements of point defects as well as the line defects. So once the dislocation is stable at impurity strikes, it is hard to remove them. So we say that they are in the plastic deformation. So then we come to the planar defects. Planar defects means the defects is in the plane. So plane means the complete plane. You will have always whenever you measure the resistivity, it is really the resistivity. If the crystalline order has been there, the resistivity. The major factor for the resistivity measurement is not only the contribution, the grain boundary. So what is that grain boundary? A boundary which isolates one grain from the other. So that boundary is a defect. So that boundary we can say can be created by the antiphase domains. So the phase is different here. If we see on both the sides, there is a boundary. So you can say it as antiphase boundary. So if suppose a sequence is there, which all the arrangements are there in this side, but there is a difference here. So total plane, we have the difference. So suppose the arrangement is like ABC, 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 but if it is like ABC, ABC, BB, like that, then that comes to be the different, and then we say it is in a planar defect. So then another thing is that if we go to these are the planar defect, then it's the stacking fault. So the fault which occurs, the full dislocation splits into partials. So like we have the line dislocations here. So stacking fault means it can go to in the 3 dimension. Here the B is actually the Burger factor, which I was saying. So the region of the half and unit cell displacement in a defected region is 40. So total region is in the 3 dimension that we call as starting faults. Another is that, or we can say start with the 2 dimension and then the 3 dimension. Then the twin boundaries, that is twin boundaries means they look identical, but at the boundary there is difference. So that is the twin and they can be a mirror plane. So then also there is a difference. Then we say it, the sample is a defect. So twin is one set of dislocation and it is or it is a planar defect and there is a rearrangement in it, although they at the boundary they are different, but they have means they are like a mirror plane. Then if these defects are present, then what are the practically this we say, like suppose we are impurity in the semiconductors, like we are doping something, like we know that n-type p-type doping we do it. So those type of doping is also an impurity in the semiconductor. That impurity may be a good purpose. So p-type doping, n-type doping, that has to have known that the charge carrier, because the initial is for the students, so it is like the charge carrier increase or decrease. So the p-type, n-type charge carrier concentration. So that is all doping that helps it, but actually it is a defect in the crystalline order. So that also the impurities in semiconductors, if it is there, then that there is a donor state and the acceptor states. So those, they can change the variation in the conduction band and the valence band, that is changing because of the acceptor and the donor state created because of the doping. So those variation also, this variation, if we just click, means observe it, and later on during my course of the talk, I will just show that will play an important role, this variation of the valence band and the conduction band. So that will help us to know the how it is affecting the major changes in the semiconductors. Now, so these are the defects. So defects, but now we'll come to the, because as when the talk is started, so defects as such is important. The very example is that is the semiconductor. So the semiconductor, so we know that the charge carrier concentration, everything you can change you can play with the variation in the band gap. So that also in the work function of the material. So that those things will help in the conductivity and other electronic properties of the material. Now it comes these defects which will stay as the standard in 3D. So, but can it be possible in the 2D material? Then what is 2D material? So the 2D dimensional material, which is now currently much studied, it's a well-studied system currently for last decade. So it is the starting point is the graphene, so which is a hexagonal thin layer, or you say single layer or honeycomb lattice. So that is the graphene, which is at the beginning, the mother of the 2D material. And after the discovery, we have any material, like even in the superconductivity, everything, all 3D is going to the 2D. So 2D means you have the length and the breadth, the height means that you have a single layer or a two layer material. So that completely differs from the 3-dimensional material. So 3-dimensional, when you go to the 2-dimensional material, then what is happening? So that is a quantum confinement is happening. So quantum confinement, it is more or less, that is your, so you will have a quantum confinement. So all the density of states and all those things that will vary. So the density of states versus the energy, that graph will change. So that will be similar as your quantum wave, which is well studied in the quantum mechanics. So that 2D material, that's why because of their quantum confinement and also because of their means when you link it on to 1 dimension, 2 dimension, that means thin layer, then majority of the atoms are present in the surface. So they say that is the means there is more surface properties, they say. So that is, so one is like graphene, then maxines, then others like hexagonal boron nitride, this is TMDS, that is transition metal dichalcogenides, then the black phosphorus, all these things, many of the materials has been. And what is the graphene and its derivative, graphene oxide, graphene itself, and oxygen means you have the oxygen groups here, and the graphene quantum dots can be present, means it is a graphene but having a zero dimensional layer, and there is a reduced graphene oxide, so that some of the oxygens present in the graphene oxide that gets reduced. So why it is so important? Because of the very high charge carrier concentration as compared to its bulk. That is the first thing, and the other properties because of the quantum confinement. So then it comes what is a dye. One is the graphene, as I said, that is the you have this single layer and it has a like zero band gap material. Then it comes to transition metal dichalcogenides. Here the transition metal in the periodic table, and dichalcogenides comes here. So the combination from here to here gives you the dichalcogenides. Why dichalcogenides? So it is not a single layer, rather than 1x, 1 between M, and the complete is called was one layer, and between them, so the normally interlayer capacity difference either in graphene and all those things goes from one start with 1 nanometer or 0.65 nanometer in case of this MX2. That means, so this transition metal can be M. So normally studied is molybdenum form, that is tungsten, and X is like not oxygen but SACT, that the dichalcogenides. So these are the materials which are well studied. So, but what is the difference between the graphene and this one is that the graphene is like it has the zero band gap, whereas it has, whenever you want to use it for solar cell or some applications where you need some band gap, it is not possible. But that is compensated in these materials, which is MX2, that it has some band gap which is indirect, but because of the quantum confinement, it is changed to the direct band gap of the suppose 1.2 eV or something like that. It points to 1.9 eV when it goes to the 2-dimensional. So this indirect band gap actually really not helpful, but in the bulk form, but it becomes a direct band gap. And because the band gap increases when there is a quantum confinement happens. So when it approaches the single layer and its large surface area defects present, modify the physiochemical properties. Now, let me say that because of these layers, interlayer bonding is van der Waals, so it is easier to remove. So that's the main characteristics why it is. And then I can say about the structure of HBN. HBN is a hexagonal boron nitride. So hexagonal boron nitride, this is we have seen a graphene, but it is called a white graphene. Graphene, we say that graphene is a honeycomb lattice having the hexagonal bond structure, and they have the layers. But here in case of hexagonal boron nitride, you have a boron as well as the nitrogen. But the difference is that the graphene has a zero band gap, whereas hexagonal boron nitride has a band gap of 6 eV. So these 2D materials in TMDC was saying that it is between 1 eV to 2 eV. In graphene, it is like a 0 eV the band gap, and these materials have the band gap of 5 to 6 eV. Now, 5 to 6 eV band gap is very high. It can be considered as an insulator. So initially, HBN was used particularly as a substrate to grow the graphene material, because they have the mutual lattice compatibility. So, but later on, these materials are very useful for quantum optics. So those materials are now in studies. So you have this material can be in the form of zigzag, means there is some they can be in a zigzag nano ribbon, or can be nanotube, or can be fullerene. But but it's well studied fullerene is from the graphene. Well studied fullerene is from the nano ribbon is from graphene. But here also these materials also they can nanotube, and also these hexagonal boron nitride they can form. So the B and N atoms are strongly bonded in 2D honeycomb lattice, thermally and chemically stable, and wide band gap of 6 eV. So why this band gap is so important? For any optoelectronic studies, optics, that you need to absorb some light or any variation, that band gap plays an important role. So here the band gap modulation is an important, whether the band gap increase or decrease or make it from indirect to the direct. So all these factors important for the application point of view. So similar to the defects which we have seen, like 0D, 2D, one means 0-dimensional defect, 1-dimensional defect, and 2-dimensional defect, like point defect, line defect, and this. Here also, although these materials are 2-dimensional materials, there also this type of line defects can be occurring like this, and also can be like pattern defects can form it here, and also the interlayer defects can be there. There can be also point defects, the stone wells defects, dislocations are there. So 0D, 1D, and 2D, like a folding or wrinkling. So even if there's a 2D material, but there also we can have a different, like heterostructure can be formed. So that also gives you a type of defects. So we can say that the next which will go, that the defects are inevitable, because whenever you synthesize the sample, it is not possible to synthesize very well, means purely single crystalline and whatever you aim like this. During the synthesis, it is inevitable that defects will be generated during synthesis, transfer, and application. But it is very useful if we manipulate the defects. Manipulate means if we engineer the defects, we control the defects, put the defects in particular desired places. Suppose there are vacancies and all those, we put the defects in desired places, then it will be very useful. So desires are not always bad as we think in our everyday lives, but they can be useful very. So now I'll come to the thing that defects in graphene. So one is this Stonell's defects. So this type of, they're hexagonal, but you see that there's something here, it is not 7 and somewhere it is just 5, but either it should be a hex, 6 bonding should be 6 numbers, but rather than it is somewhere it is changed to the Stonell defects here. And you can have a single vacancy defects like that in case of your graphene. Also, you can have multiple vacancy defects. So this is the graph is from the Sleatal, and one of this as also contribution in one of my students' work, so which is just written here. And vacancies in molybdenum disulfide. Molybdenum disulfide corresponds to the transition metal dichalcogenides. So transition metal dichalcogenides, that is one of the means we work in so many materials like molybdenum disulfide, graphene, WH2 also wolfram sulfide, disulfide, but like I'm just saying some of the words because which as best I can explain. So that whatever the students have done, so it is here another student's work. So that is this molybdenum disulfide. What are the defects it can be? It can be so it is a TMDC material, transition metal dichalcogenides. This is transition metal. This is here. So what can be the defects? One is the vacancy corresponding to S. Vacancy corresponding to di vacancy, 2S are not there. MO and S2, so MO1 MO, and then S is the vacancy. Then vacancy corresponding to MOS3, there can be 3, and vacancy when the MOS6. So so many vacancies can be produced in, and these vacancies normally creates this S vacancy 2 to 3 eV, and for molybdenum vacancy 8 to 9 eV of energy required to create this vacancy. And so if these are the vacancies, then I will tell the next that there is a defects in HBN, that is the hexagonal boron nitrate. So boron nitrate just now we have seen, which has the band gap of 6 eV. So that is that what are the defects? This is a similar kind of Stonell's defect as you have seen in the previous one slide back. That is the Stonell's defect, that here it is not the hexagonal, it is just 7 bonds, and somewhere it is just 5 bonds. So yeah, so those are the Stonell's defect. Then it is a boron defect. And then the tetrahedron defect, that here is a tetrahedron is created, and somewhere this is the anti-site defect. Then you have the anti-site means the place where one should have, ideally this should have, I have not told before, in general term also anti-site means ideal place of, if it is a 2-atom molecule, then ideally wherever that H and Bn should get placed, if they are not in the same place or they are interchanged the place, suppose here the bonding is there 6 bonds, but this place ideally should go to your, as you have seen here, it should have gone to the your boron. So nitrogen. So instead of going to nitrogen, there is a combination of only boron like this. So this variation is called the anti-site. Then another is your like a interstitial vertically bound. Here different 2 layers are there, but in between ideally there should be a bonding in a different interstitial is there in here, and another is interstitial diagonally bound in the bilayer. So this is also the defects in HBN is there. Now, so many defects can be present during the synthesis or you can generate. So if the defects is present, as you know that, which is basic fundamental, we know everybody that whenever we prepare the alloy gives a different property from the original component material. Like you have the there is a very big difference between a steel and the difference between the iron, and steel has much more application as compared to iron. So this way, similarly here, if we, so it is one kind of, either you mix it with something or you generate with some defect. So so those can be very useful material. So now what we are going to tell that ion irradiation, although I have written shift ion irradiation. So one of the technique which will now in general talk on your defects and then the 2D materials is over now. Now I'll go to some of the research work of mine which is related to it. So then we are doing this swift ion irradiation, which is a tool for controlled and targeted ex situ defect generation. Ions induces defects and latent tracks. One thing I have just not told you, that is a latent track. That word is not normally used when the people study only defects, but people who are used to this type of ion irradiation studies, so they use this latent tracks. Latent tracks means a successive series of defects or a line defects in a line for a long period. So that is a longer period than the size of the defects, means the length is much higher than the width of the defects. So then you say it is like a track, means you have a pipe of defects which are there, but normally it has a conical shape. So those things are this swift ion irradiation can do. So now we'll come to that point, that what is this irradiation? That it is because the audience, I'm not only telling to the people who are doing with the ion beam experiment, but like to the in general. So that's why to start with that swift ion irradiation means it is an ion irradiation that we are using some ions which are accelerated with very high energy to induce the defects in these materials. That defects can be produced like they can be with a very high energy, means the ions are coming at a very high energy, like 100 million electron volt or more than that, one say about 120 electron volt or that. And this defect, when these ions go through it, they come with a very high energy, and once they go inside the atom, they can produce they will naturally during the collision they will lose the energy. That can be, they either can transfer the energy to the electrons or to the nucleus. So that is called as this energy loss to the electron or energy loss to the nucleus. So those nuclear energy loss, and this as explained that also creates this point defects and vacancies. And here this everything happes in a very fast time, and also in picoseconds and femtoseconds. So those happens means that suppose it is at a very high energy in MeV, then it is mostly that the incident ions that give the energy, transfer the energy to the electrons, then the electron transfer the energy to the lattice. That lattice that happens very that knock the electrons, then have an electron cascade, and that happens in the 10 picoseconds. And because the lattice, after getting so much energy, naturally the energy will be converted to heat. And once the lattice has a heat, then what will happen? If it has the conductivity, then that will pass through. If it doesn't, it's a good conductor, then that area will get defected, means that will melt or something will happen. So, and everything will occur in a very short time of 10 to the power minus 12 seconds, or minus 14 to minus 12 seconds. So then this, another is, so they produce some kind of defect. So lattice naturally will get defects. So this type of defects can be produced. So that they say that the ion beam, they can produce with different energy, and sometimes there will be a sputtering, because when it passes through, it will create a disorder. This kind of we saw the defects here also. These disorders can be produced. But what is the beauty here is that you can have the control over how many ions per a unit area per second you can incident, so that you have a control. There is some minimum amount of 10 to the power 9 ions should go per centimeter square per second, but after that you have a control over it. So if I know the control that I can produce per second this one, then I can have it. This type of disorders, I can have it some disorder distance I can maintain. So that is the control creation of the defects. So the control over nature, density, and distribution of defects, that is used. This facility is used at the IUS in New Delhi, and these are the things which I have said about. And this ion beam also can produce the recoils, and some of the atoms naturally on the surface, they will get sputtered. From the beneath will also get sputtered. Some can get backscattered, and there can be some depending upon the energy of backscatter, or rather for backscattering, And this electronic interaction also in general did nothing with the ion beam at 120 MeV. It can have this general slide can say you about any energy of ion it comes. So that can induce also X-rays and electrons. And this electronic interaction can happen. So if with some velocity and a kinetic energy it is coming, so that can induce so many things with a nuclear interaction or an electronic interaction. So normally we explain it in this basis. I don't know whether I should go in detail. So one is the Coulomb explosion, means that the ion is passing through and it is like exploding it, and it is if it is a positive ion, then it is repelling it positive. So you have a wake up defects here. They are not. So you say it is a Coulomb explosion. Another is a thermal spike, as I said, because of the thermal energy which is they are carried with the ion that is transferred to the electron, and that leads to a localized melting, and it can produce some stress there around, and some plastic deformation occurs, and all those things happens in a very short period, because thermal is involved, because your carried kinetic energy is converted to heat energy, and heat energy is resulting in the disorder of the system. Now so this is so we'll start with as much I can just cover up. So that is, we'll start with what is, if we irradiate with graphene, because as I said, with 2D material, so if graphene is irradiated, so normally the graphene is a CVD grown. So CVD grown means chemical vapor deposited graphene samples. They are of like 1 centimeter by 1 centimeter substrate, and the layer is like a single layer or bilayer samples. And we use the swept away irradiation of 120 MeV silver ion. So as the facility gives it, IUSC, Inter-University Accelerator Center, Delhi. And then as I said, that this is the minimum. That's why I told that this much is the minimum. If we want also, we have to go that 10 to the power 6 ions should come. It is not possible. So with that current, it's the initial, this much we have the minimum flux to be required. And what we can give that this much 511 means 5 into 10 to the power 11, 1 into like this type of number of ions per centimeter square. That's what we have a control over it, that this much of ions should get incident on it. So this much of defects can be produced, and the energy will decide what kind of defects can be produced. So this is normally, so what we found it, if it is there. So this work is one of my students' work. It is in surface interface. Okay. So So here, what is the changes here? There is a changes in the XID peaks. So XID, you have the pristine sample, and there is a broad and weak peak due to multi-layer bands, become broader with increasing fluence. Fluence means number of ions per second that will increase flux into time. That minimum this much of ions per centimeter square per second should be an incident. If I increase the time, then that means dose I am increasing like that. So this gradually decrease in the crystallinity, which is expected here. And here also we have the UV visible transitions and UV visible optical, because as I said, it's the optoelectronic studies, means we said about. So we have done this UV visible absorption as well as the FTIR. So FTIR between 1000 and that says about the CO, carbon oxygen stretching bond effect, and the peak at 264 nanometer, that says the end-to-end transition. So this type of Raman spectroscopy, because Raman spectroscopy gives the exact signature of the defects and the exact signature of the graphene, whether it is produced or not. So that gives about this 2D peak at 28, that's 2D peak at 2680. So that centimeter inverse. So that gives the 2D peak, means it is a like good pristine sample, is a good like a good graphene sample, and these are the peaks of the D and the G peak, and these are the defect identified peak, and this is the peak corresponds to the stretching bond. So, and this TV peak, normally Raman spectroscopy, why it is given that this is the spectrum that gives about the signature of the peaks here. Then the defects are there or not, that is the defect activated peaks. One is the D, which is 1345 centimeter inverse, which is seen here. And another is the D dash peak, which is occurring as 1625. So that gives you D dash peak. And then G peak is that, and I to D by IG is 2 to 4 for single layer graphene. ID by IG, actually this intensity of these peaks normally which will use later on, that it gives more about the defects. And these are for the relations ID by D dash, means two types of defects. So what is should be for the grains and the grain boundaries. Now what we actually get it, if I have to show you so many things. So actually what we find here, that we think we can find it like we have the 2D peak, and the 2D peak as the G position we have seen for different ions, different fluences, these samples. So what is the 2D versus G position, as well as we have the defects, the variation of area, FWHM position and position of this 2 peak in depth analysis of the Raman peak. And what we find it, I can say that we have a absence of any G and 2D peak. First, we find a strain. So what is this strain? Strain is that in the variation in the Raman peak, the Raman peak is that if there is a variation in the G and 2D peak, so here the strain is there. So strain is calculated change in the G or 2D band frequency of irradiated graphene with respect to the pristine graphene. So Raman peaks gives like naturally, as you have said, correlate with the, like if you insert a series of defects inside the material, naturally a strain will be induced in the material. So that strain can change the properties in the not only in the mechanical, also in the optical, as you are seeing in the Raman. So Raman will say that whether the strain is induced in it or not induced in it. Particularly here, the strain is not that much. So that because it is not, the peak splitting is not that much. And we have also seen that the magnitude of the Fermi level, so that will say about the Fermi level EF, that is the in the graphene Fermi level, which is related to the G peak position like this, that we can find it at 2EF equal to the variation in the delta WG by 21, not 2I. So this delta WG is the frequency of the G peak position of doped and pristine graphene. We have used, and I have used the word optoelectronic. That optoelectronic means actually we do the electronic study, means the change in the variation on the surface because of the Kelvin probe analysis. So that is the scanning Kelvin probe. scanning Kelvin probe is a unit which measures the work function of the material. So work function of the material is related to the your like you have the binding energy, and that phi sample is related to the conductivity, conducting band energy, and the Fermi level energy. And actually we measure in terms of the VCPD. That means this is like a principle of parallel capacitor. So we provide some current, and there is the electrons from the, like if there is two materials, like we have a gold tip, like we do it in atomic force microscopy. Here it's a gold tip, which, as we know, the work function of the material, and that work function, and you have a material whose work function to be determined. So that is phi sample and phi tip, you know it. And when the two materials are kept very close to each other, so there will be a electron flow will occur. So that will be, now there is a flow will occur. So when the sample and the reference, so then they will be equalized. Now you provide some other biasing voltage so that there will be a stop effect. So that gives how much voltage you provide. So that indirectly helps that EV as how much is the difference between phi tip and phi sample. So phi tip is known factor, that is the metallic tape gold work function. So 5.1 EV. So one can determine the phi sample, that is the work function of the material which we want to know. So that is the scanning Kelvin probe study, and the work function of graphene. That's so we will normally we find the sample. So we vary that. So with this, the contour diagram says about this work function of the material. It is actually the color is as per the variation as we are seeing. So in different area this color. So then we take it in an average wise, what is, suppose here this color is in, so that gives the value of averaging the value, how much should be. So EF is calculated from the value, like WF is calculated from the VCPD, and then the EF is calculated from the, which is inverse of it, and the EF is calculated from the split of the GPIC, and we compare it, that the variation in the WF as well as the EF, because we know that the Fermi level and the work function, they both are related, and if we plot it, that also, just 1 minute, whether it is there. So they also go similar parallel, EF calculated from the GPIC variation and WF calculated from the they both goes to the Fermi level, goes to the valence band. So what we observe in this case, we have done some calculation, like the sputtering yield in this, how much electron this sputtering is occurring from the trim calculation, and also this computational result that which we normally do, this ACSN, that is the electronic energy loss and what are the defects, and the vacancies calculation, that all are the simulated results. And this sputtering yield, that also says what happens there. So what we expect, that there is a doping means what? That we say that because the substrate is, this graphene is deposited singular graphene on silicon dioxide substrate, and the range is very high. Some of the oxygen atoms here are getting inside it. So that is the oxygen recoil distribution that is getting penetrated in the graphene. So that creates one type of doping in the graphene. So that graphene P type of doping is occurring. So that says about which helps in the doping occurring through the substitution of the carbon atom in the graphene by small fraction of spotted oxygen from the SiO2, and this spotted oxygen radicals formed by ionization during strong electronic excitation. And so next I will just tell about some, a molybdenum disulfide things. So molybdenum disulfide, that is the transition metal. Here it was the graphene I said. So similarly, they are irradiated with different ion beam energies, and these give some different like the energy loss. And they are also, this is a previous work as compared to this one. So the previous work says that there can be two prominent peaks. So this is a so here we see that the peaks systematically changes. So so there is changes in the this case. So you say it is a tensile strain is occurring. So the pressure shifting and break. So that says about the tensile strain, and also we know that the strain is normally calculated by, in general, for other materials from XRD, and we have probably, so there also the XRD from the strain is also calculated from this William Hall calculation, that is the WH formula, which is used normally from in general sample. So whether you exhibit the Raman peak change or not, so that, and tensile calculated from XRD here, tensile calculated from this one. So that goes almost matches in the similar way for the A1G mode. So A1G mode is like a outer plane vibration, and XRD is also the C-axis peak, and E1-G is the in-plane vibration of the means MOS2. So there is a vibration MO here. This type of bond is the vibration is MOS2, and the other one is variation. So this says in the variation in the in-plane strain and the outer plane strain, that is in the A1G peak, and this one the in-plane strain. But when we compare with that of the work function is similarly measured using the scanning Kelvin probe spectroscopy, microscopy. So that gives a work function variation here, and the variation, the complete work which we say that if outer plane tensile strain, and you have the work function here, this one, and out of plane tensile strain goes like this, but your in plane tensile strain and this one, that goes very parallel to each other, and so they are linearly proportional to each other. So this work says how we can just prove that the strain in the material affects the in plane strain in the material affects the work function of the material. So we have Raman spectroscopy gives you the optical, and the electronic properties is the surface electronic properties, because the work function is measured from the surface, and you have the that they are linearly proportional. And also we find that they are also from TM studies that there are tracks created in these materials, and the defects which are produced, they can be seen from the these are the materials which are initially, and then there can be tracks produced in these materials. So then I'll just tell about what we have got in 2D HVN. So the HVN, as I said, they can be synthesized by either by CVD or by the chemical method. Here they are prepared by the chemical method. So this CVD chemical method, what we have done with hexagonal boron nitrate, now we have not used the swift heavy ion beam, rather than we have used very low energy ion beam, which is a 30 kV nitrogen ions. So this nitrogen ions, that is also expected, as we have seen this previously, that what kind of vacancies can be created. So this is one is the boron vacancy, another is the nitrogen vacancy can be created. So, and we'll see which vacancy can be easier to produce. So, and which will outweigh the other one. So that is this type of defects. So boron nitrate nanosheets are irradiated with 30 kV ion beam, and they were published in Applied Physics Letter in 2021. So that we have seen the same variation with work function as well as the variation in the properties of Raman spectroscopy, UV visible and XRD, and the same simulation results that gives about this, which is the standard thing, that is the range, how much distance the ion can penetrate, the sputtering yield, how much vacancies they are produced, and the nitrogen vacancy. So we see that the kind of boron vacancy, the possibility to create the boron vacancy or the nitrogen vacancy are the same, but the boron weight is more than that. So the boron weight vacancy outweighs that. So the mostly is probably the nitrogen vacancy. So that ACSN plot we have done, and the B and N vacancy we have done. And ACSN plot, so differential B and N vacancy profiles, and the surface layer of B and NS is affected by SN to create B and N vacancy. This enhances the NN distance along plane and reduces the interplanar distance. So because of that, it reduces the interplanar distance D in the B and NS means boron nitrate nanosheets. Actually, that I should have told from the beginning, sorry. So that was the, instead of hexagonal boron nitrate, we have actually done the boron, means it is hexagonal boron nitrate, but some of the nanosheets, it is 4 to 5 layers. So that was from the characterization from the Raman shift, it was characterized how many numbers of layers are there. So number of layers is around, just 1 minute, it's a 4 to 5 nanosheets. So the number of 4 layers of BNNS, so boron nitrate nanosheets, you have done it. and that is used by this calculation. And UV visible measurement also says that the band gap is there or not, how much is the band gap, whether it is changed, and what type of crystalline and irradiated films it is there. And variation of band gap with also refractive index, also we have done it with AU minus 1 irradiated. So the band gap and refractive index inversely correlated it with N equal to a refractive index 17 minus EG by 5. So that is used. So that refractive index calculation also can be used for the means that we have taken for the third B semiconductors, because BN and XID, as I said, so it is expected to change the 002 the D value. So that strain is calculated here using the value of how much is the D is changing. So from the William Hall calculation, so that is ln equal to B by 4 tan theta, B equal to the FWHM, and theta is the angle. So strain is calculated, and also we had done this strain under D. So as the ion fluence enhances the compressive strain inside the in a perpendicular direction, a tensile strain comes into play in the in plane direction, and that creates a possibility of increasing atomic distance. So this also we have done the similarly the SKPM imaging, and that also the WF was found to be 5.8. But what we have found it that the strain is calculated here like this, and the WF values, and we have plotted it the WF value and the compressive strain here. So this strain work function value and the strain, and they goes in the inverse ways, they are related. So, and we have done the theoretical calculation that whether using the strain, so that WF will, how it will change. So theoretically it says that the delta W should go in a negative way. So that compressive strain lambda becomes negative, such as a compressive strain. So that gives lowers the work function. So we find it that compressive strain will lowers the work function of the HBN. So in the summary, I can say that the low energy ion beam that creates the vacancy in BNNS in this material. So because it is in each part in a different way. So I think I cannot go to the next, which is I just recently applied surface science, it's a graphene oxide TI2. I'm not going. So let me just go to the end, and let me tell that means thank you for your kind attention. So thank you all.
Thank you so much, madam, for sharing an elaborate explanations about different types of optical studies and defects and nanostructures, manipulation strategies, and investigation on remote spectra also. So there are some questions also in chat box. I will read one by one. So questions is from Dr. Radhakanta sir. First question is: does the shock wave due to ion beam radiation create more defects in the crystals?
Just let me, can you just give me a minute? Let me go, and chat box, it is there, right? So,
Yes, ma'am.
okay. Okay, so many things. Okay, does this shock wave due to ion beam radiation create more defects in the crystals? It is expected, means more defects in the crystals means actually in crystalline, as I said, the defect creation is, means if it is purely crystalline, it is much more difficult. And shock wave means shock wave due to the shock wave induced due to the ion irradiation, or what is the question? I cannot understand. So,
Radhakanta sir, please ask a question. I think this is the question asked by audience.
okay, thus so many questions are there. So I will ensure that I am being interested to be one layer or two layer sample. So okay, can I just then the other part? So okay, so if we say that it can induce 2D layer or few layer, it can be seen in your TM studies, right? Initially, whether your sample is one layer or single layer, that you can just do it from the TM, and then whether the defects are produced or not, that you can see from the TM studies. Then the third question is, how is the number of ion beams related to the number of defects produced? Is there any mathematical defects? Okay, actually a single the defects, the number of ions present, that with how much energy, that is clearly we have a relation there. The defects, how much defects produced. So each ion will come, one ion will come and create one defect only. But with what energy it is coming, that is important. So that will, we have a systematic mathematical relationship there. What is the, how do we differentiate between Raman peaks due to defects and due to impurities? Because impurities itself is a defect. So, so this question also I cannot understand. That impurities, it is, so if the question is whether you can differentiate between the impurity induced Raman peak and the ion beam induced defects the Raman peak created, so you can do it with the pristine sample. So initially, whatever you are prepared, take the Raman peak of it, and then when you introduce the do the ion irradiation, then also you can do it. So then you can find it out the difference in the defect. And the time Ayush Kumar Jana, what are the real life application of graphene? ये तो आप Google में देख सकते हो. It has a much more application starting from your GFET, which is a graphene field effect transistor. Graphene can be used in solar, not in solar cells. Graphene of all optoelectronics. You have this thing. You can see like your TV will be also a film of graphene. So wherever you need the charge carrier concentration, that is why you need the gallium arsenide. So because of the charge carrier concentration, so the charge carrier concentration, which is actually induced due to the quantum Hall effect, so that because of the very, very high charge carrier concentration, 2 lakhs, means then you use the unit. So that can make it more conducting and everything can be used. And also its magnetic properties. So it has a lot of application, is it? Okay.
Thank you, ma'am.
Okay.
If you want to tell something, please carry on.
No, it's over. Actually, I was trying mostly like initially I started it because the audience is different from different place. So I didn't want too much to tell about my research work. So some of the things I have just told because so that's all.
Thank you, Tanuja, for the nice talk.
Okay, thank you. Okay.
Yeah, thank you, ma'am, for
Okay.
beautiful answers and presentation.
Okay, I'll just send it. Okay.
Yes,
So,
ma'am.
okay, so I can just make it is stopped, right? It's closed, right?
Yes, madam.
Okay.
Once again, on behalf of OUTR, I would like to convey many thanks to Professor Mohanty Madam for her valuable contribution in this webinar. Thank you so much.
Our next session will start at 2:30. So all of you please join for the last session and last talk.
From 2014 to 2017. He is awarded with DHT Inspire Faculty Award 2017, Gita Ujjankar Award for Best PhD Thesis 2014 to 15, and Honorable Mention in Rahul Basu Memorial Award for Best PhD Thesis in High Energy Physics 2014. Recently, he is also honored by Young Achiever Award Day Symposium on Nuclear Physics 2022 at Cotton University, Guwahati. His research interests are in the theory of high energy nuclear physics, thermal and blast wave models, relativistic hydrodynamics, and the physics of strongly interacting QCD systems. He has contributed actively in more than 36 papers with high impact parameter journals as PLB, PRL, etc. With this short biography, once again, let's welcome Professor Amresh Jaiswal sir to deliver his presentation before us. I request you sir to start his talk. Thank you, sir.
Thank you, Deepika, for the nice introduction. And thank you, Madam Babita Ojha, for inviting me to give this talk. I'm very happy to actually be here and present this sort of very introductory level talk on quarks, gluons, and the quark-gluon plasma. So let me start from the four basic forces that we are all familiar with. The gravity and electromagnetic force. These two forces are the ones which we feel directly in our daily life. Gravity, as we know, helps everything keep attracted to Earth or to any massive object. And electromagnetic forces are forces which are due to the electric charges. So essentially, that's what keeps the atoms and electrons bound to each other. And the photon is the carrier of this charge, this force essentially. Okay. And then there are two other forces, the strong force and the weak force, which we don't directly feel, but they are of course indirectly present in our daily life. They are the ones which keep the nuclei bound and stable. Okay. And most of my talk, I would be essentially focusing on the strong force and its consequences. Okay. So just to get into a little bit more details about what the four forces have. So for example, there are so for electromagnetic forces, the electrons and nuclei, they are attracted to each other because of the opposite charge. Okay. This is different in gravity. In the case of gravity, no matter what charge, in this case, the charge will be mass for gravity. So this matter or antimatter, they always attract each other. Okay, that's what makes it a little bit complicated compared to electromagnetic force. And for the strong interactions, we have the quarks, which are bound to each other by gluons. Okay, the gluons are similar to photons, where quarks are similar to electrons. The only thing is that there are the quarks are there are three. I mean, gluons and quarks are not just one. Like in photon, there is only one carrier. Gluons, there are 8 gluons. Okay, and then there are generation of quarks. The up and down quarks are the ones which forms the nucleons, which is neutron and proton. And then there are other hadrons which has different other different quark flavors. And weak interaction is something which actually helps in decay of nuclei. So for example, burning of sun, neutrino interactions, also this nuclei that we see are due to weak interaction. Okay, and the carriers are W and Z bosons, and they happen between so this processes the weak interaction also takes place between the quarks. Okay, and as well as leptons. So we will see in the next slide the unification of fundamental forces. So these forces that we know, the electricity, magnetism, and light, they are all. I mean, electricity and magnetism were all unified into electromagnetism long back in 1864, and then not so long back. I mean, 1970 is not that long back. The electromagnetism and weak interaction was actually unified into electro-weak interaction. Okay, which was this Salam-Weinberg-Glasgow model, and we also have the strong interactions. Standard model is not a unification of electroweak and strong interaction. It's just a compilation of the theories of strong and weak, strong interaction, electroweak interaction. The unification is termed as the grand unification theory, but we don't have a good handle on that yet. Okay, and then we have unification of universal gravity, the Newtonian gravity, which we know, gravity on Earth, and celestial mechanics, as well as space-time geometry, which was proposed in special relativity. So unification of these two is the general relativity, theory of general relativity, and unification of the theory of standard model and general relativity is something which is the holy grail of physics. I mean, all good brains on Earth are trying to unify these two theories, and I won't say we are close, but yeah, I mean, there are many leads, actually too many leads to follow, and still it's very out of reach. Okay, and okay, so here are the standard model of elementary particles. So we have generation of quarks, leptons. The generations are from up to down. I mean, we read it, the generations like this. So up and down are the first generation of quarks, charm and strange are the next generation, and so on. So there we have these 6 quarks in the standard model, and then we have similarly 3 generations of leptons and 6 leptons. Leptons are electrons and its electron-like cousins like muon and tauon and their corresponding neutrinos. These are the ones, the leptons and the neutrinos, they interact via weak interaction. Okay. And then we have the gauge bosons, which are gluons, photons, W and Z bosons, and the Higgs boson, the one which gives the mass. This is the only scalar particle in the whole standard model. Okay. And of course we should have graviton as well in the theory. That is not well understood. This is the one which is in the general theory of relativity. When we are supposed to quantize it, we will have graviton. The only things that we know about it is that it's going to be a tensor field, and it's spin 2 particle and so on. But I mean, the quantization, we are nowhere close, right? And yeah. Next slide. Yeah. So in this unification, what I will focus on in today's talk is strong interaction. And this was the theory of strong interaction was developed in 1970s. And that is the theory of quantum chromodynamics. So now it is well established that QCD is the fundamental theory of strong interactions. Okay. So the main features are that there are many hadrons, which are made up of elementary particles, and the elementary particles of QCD are quarks and gluons. So hadrons are all baryons and mesons. So they are all together called hadrons. Baryons have 3 quarks bound by gluons, and mesons have 2 quarks which are bound by gluons. They all together are called hadrons. Gluons are the mediators of strong force, similar to photons that we know for electromagnetic force. And but there are, and of course quarks are the ones which carry the color charge. Okay, there is only one electric charge in case of in electrodynamics, but the difference from electrodynamics to QCD is that there are 3 charges, color charges, compared to 1 electric charge. And because there are 3 color charges, this makes QCD very, very interesting. So because of this, the fact that it has 3 color charges and 8 gluons, which mediates between the colored particle, leads to confinement and asymptotic freedom of QCD. So what it means is that the strength of interaction in QCD, okay, it depends on, it also, we know that it depends even in QED. It depends on the energy scale of the interaction, which basically follows from some very complicated renormalization approach. But what I'm trying to say here is that QCD has a different behavior compared to QED. So what we see is that one of the confinement property tells me that the color charge particles we cannot isolate and we cannot directly observe. So for example, the quarks which are colored charge particles, we cannot separate them. We cannot observe single quark, but they have to be bound into hadrons, which we can observe. Okay. Whereas asymptotic freedom, this tells me that the interaction between quarks and gluons, as the interactions become very, very weak as you increase the energy. Okay. So these two, so confinement is at low energy. At low energy, I mean at the energy that we would like to observe, we cannot observe colored charge particles. And asymptotic freedom tells me that at very high energies, they are supposed to be free. The quarks and gluons should be free. Okay. And because we have both these confinement and asymptotic freedom in QCD, okay, this leads to very interesting thermodynamic properties. And thermodynamic transport properties we will see later, but thermodynamic properties are very interesting. So what I show here is the QCD phase diagram. Okay. So on the x-axis is the net baryon density, and on the y-axis is the temperature of the temperature at which we are observing. Let's say, I shouldn't say temperature of what, but rather the temperature at which we are observing, and the baryon density. So for example, nuclei has, so this is at 1. So in the sense that 1 is, okay, what I should rather, this net baryon density is measured in terms of chemical potential, and this 1 is the 1 GeV would be the mass of the one nucleon. So nucleon, one neutron or proton. So nuclear matter is around 1 GeV chemical potential, because that's the amount of energy we need to produce one nucleon. Okay, and these arrows are experiments. So the experiments at RHIC and LHC, the Relativistic Heavy Ion Collider at Brookhaven National Laboratory and Large Hadron Collider at CERN, they take the nuclear matter and heat it up to very large energies, very large temperatures, or at an energy level of 200 MeV. Similarly, the fair energy is supposed to heat up the system as well as take it to large chemical potential, large baryon density as well. Okay, so both increase of chemical potential and temperature. Okay. Now, what I will like to draw attention to this yellow band. This is the region of where QCD has a phase transition, a chiral phase transition from quarks and gluons to hadrons, okay, which ends in a critical point. And then there is a crossover. Okay, so the general understanding is that hadrons behave very like a weakly interacting gas of hadrons, because they are color singlets, because the colored charges or quarks are bound inside hadrons, so they are color neutral particles. So they interact very weakly because they are color singlets. They interact very weakly and they're like gas. Okay, whereas when quarks and gluons are deconfined, then they exhibit liquid-like behavior. So basically, if I come from high temperature to low temperature, the QGP, which is a liquid, goes to hadron gas. So this is a very funny system, in the sense that if I cool a liquid, it becomes gas, which is very counterintuitive to what we see. When we heat water, it becomes gas, but that's completely opposite to what QGP does. Okay, the behavior is a bit funny in that way. Okay, and so quark-gluon plasma. What is quark-gluon plasma? It's a new phase of matter which is created at sufficiently high temperature or density. So, for example, if I were to collide two nuclei with a very high energy, we can accelerate two nuclei and then collide them, then whatever energy is gained by the nuclei, they will be deposited in a very small volume, which leads to increase in energy density and therefore temperature. So the QGP is supposed to be created when we collide two very high energy nuclei, and in the lab frame you see QGP is created. Also at high densities, so the core of neutron stars are also conjectured to have QGP in the core. And of course, QGP, because at very early universe, the universe was very hot, very high temperature, so QGP existed in very early universe, and it may still exist, as I said, in core of neutron star. And such extreme conditions we realize by colliding nuclei. So we want QGP, we have to collide heavy nuclei, or recently people have also, people are at least guessing that there are QGP even in small systems like proton-proton and proton nucleus collision, but at least in heavy ion collision like collision of gold-gold or lead-lead nuclei, we know that we form QGP. So what happens in this collision? So collision, this transforms a fraction of the whatever kinetic energy the two nuclei are carrying into heating the QCD vacuum. So then if the QCD vacuum is excited, then we will have production of quarks and gluons. And so the C quarks, what we call inside the nuclei, would lead to the C quarks will be manifested in this heated vacuum, and then we will have a system of quarks and gluons over a relatively larger volume, over the volume of a nuclei at least. Okay, and that is what is QGP. So, and essentially that means that we are probing very early universe by creating QGP. We're trying to understand what happened in very early universe, and ultra-relativistic heavy ion collision, this gives us the chance to create and study different phases of QCD. Okay, And it is now believed that QGP is formed in heavy ion collision experiments and at RIC and LHC. Okay. This is an aerial view of relativistic heavy ion collider at Brookhaven. So there are large rings where nuclei are accelerated and collided, and at the juncture of collision, for example, here this is the STAR experiment. They keep the detectors. There are 4 experiments: STAR, Phoenix, Phobos, and this one is supposed to be, the Brahms is supposed to be here. Yeah, 2 o'clock. So Brahms is here. So there are four such experiments. By experiments, we mean that you put the detectors around and they observe whatever comes out in the collision. So the collision happens at these 4 places, and the detectors observe whatever is coming out of the collision. Okay. As we can see, the detectors, since there is a beam line, so the major part of the detector is supposed to be transverse to the beam line. So what we observe is majorly going to be what is coming transverse to the collision. Keeping detector along the beam line is not actually feasible. So you can make it. Keeping detectors perpendicular to the beam line is not. Because we have to keep the beam line. So basically, what we observe is what comes out, from the sides of the beam line. So basically, transverse to the collision axis. Okay. Traditionally, collision axis is considered to be Z axis. Okay. And the collision at RIC happens at 130, 200, and now also there is a beam energy scan which has at very varied energies of collision energies. Okay. So what do we see in the collision? The initial state, because the nuclei are very fast moving, relativistic, ultra relativistic to be precise. Okay. So you really see very thin Lorentz contracted pancake-like nuclei. They're no more spherical in the lab frame. They're very thin Lorentz contracted because they're along the motion they're contracted. Okay, and they collide, and in the collision zone, then you will form this. The energy goes into hitting the QCD vacuum, and you form QGP, and that evolves. Now this evolution is what we would like to study. So this evolution is what carries the information about what is the properties of QCD, at least at finite temperature. Yeah? So we would like to study this evolution. So one interesting, at least the most convincing signature of QGP was the elliptic flow. So what is the elliptic flow? So Z-axis is the collision beam axis. Okay, so the Z-axis here is perpendicular to the screen. Okay. The 2 nuclei, the brown and the yellow nuclei, they are moving along Z, opposite to each other. They collide, and there is an overlap zone. Okay, the green zone is the overlap zone. Okay, in the XY plane is what we see, almond-shaped overlap zone. Okay, which is very elliptic in nature. So you can actually define an ellipticity to this zone. Okay, now, if whatever is formed in this green zone if it behaves like collectively, if it behaves collectively like a fluid or a gas, okay, then it will expand according to laws of hydrodynamics or fluid dynamics. And so a collective motion would lead to, if it was just scattering, then even if there is this shape, just scattering of nucleons and quarks without any collectivity would still appear isotropic. So you will still see isotropic momentum distribution in the detectors. Detectors are basically seeing what is coming out in the XY plane. Okay, so the fact that you see anisotropy and the fact that you see more momentum or more particles towards X direction than compared to Y direction. X direction is the impact parameter direction. That tells me that there could be anisotropy, of course, but then this anisotropy, if it was just scattering, the anisotropy will be fluctuations. It will not really be a systematic anisotropy, more focused towards one direction in all events. In all events, it will act like a fluctuation if it was just scattering. But this is a collective behavior in the sense that along x-axis, this The QGP has smaller extent. If the QGP is formed with very large density and pressure in the green zone, then it will have more preference to come out along the X direction compared to the Y direction. Okay, and this is what is seen. So we see this elliptic flow V2. Okay, and the reason is that it's attributed to the fact that the spatial anisotropy, this converts to final momentum space anisotropy because of the pressure gradient. There is a pressure gradient. So from center to outside the collision zone, the distance is smaller along X compared to Y. So the pressure goes from P0 to 0 very quickly along X compared to Y, and therefore this drives the QGP faster towards X direction compared to the Y direction. Okay, so this was actually observed, and this was the smoking gun signature of QGP. So this was the most convincing signature of QGP. Okay, so QGP is formed. Now we know that QGP is formed. Okay, and we can use relativistic fluid dynamics, theory of relativistic fluid dynamics, to study the QGP. So what is fluid dynamics? It's an effective theory. So basically, it tells me that if I have a system, then how does the system behave at large length scale, or basically long wavelength, or at large time scales. Large time scales would mean low frequency. So this is the long wavelength, low frequency limit of the microscopic dynamics of any system. Okay, so it's actually any system. If you wait long enough, everything is supposed to behave hydrodynamically. Okay, so and relativistic hydrodynamics has been used to explain all the collective observable in heavy ion collision, and this is now it is well established that QGP behaves hydrodynamically, or not only QGP, the QCD matter, whatever is formed, it goes from QGP to hadron gas, and it behaves hydrodynamically. Okay, so and hydrodynamic equations are simply conservation equations. There's nothing fancy in it, in the sense that they just are energy momentum conservation, the conservation of energy and momentum of the system, the particle number conservation, and angular momentum conservation, something which we are working towards. And I will go into more details of what angular momentum conservation means. Okay, but yeah, it's just essentially conservation equations. Okay, so for instance, the energy momentum conservation for a fluid. So we talk about energy momentum tensor. This is analogous to particle 4 momentum. So if we have particle 4 momentum, which is basically energy and momentum of particle, but now we have a fluid which is not a point-like particle, but an extended object. So we talk about energy momentum tensor, because there could be momentum of component of momentum along one direction acting in the other direction, like a shearing effect. Okay, so that's why we talk about energy momentum tensor. It's the generalized momentum of the fluid. Okay, similarly, particle 4 current, some conserved currents like baryon number conservation would lead to, so any charge which is conserved would lead to a conserved current, like Coulomb charge will have. So I represents how many number of conserved currents we have. Okay, and mu is the Lorentz index, which is the 0th component will be the charge, the density, charge density, and the jth the special component will be the current. And similarly, angular momentum, there is a T missing. Angular momentum would be just moment of momentum. This is standard definition. Remember, the generalized momentum of fluid is T mu nu. So moment of T mu nu is what we are interested in, the angular momentum. Okay, so now this is the standard model of heavy ion collision. Okay, you might have seen this already in the presentation by Professor AJIT SRIVASTAVA when he was explaining cosmology and the expansion of the universe. So the picture is the same essentially. Remember, we are still trying to mimic what was formed in early universe and how it is evolving. So the picture should actually look the same. So this is so now the Z axis is the collision axis. Again, the Lorentz contracted nuclei, they collide, and then there is a pre-Coulomb dynamics which we don't really understand very well, but there is something which happens before the QGP phase is formed. So that interaction is still people are trying to understand that. But once the QGP is formed, we know it behaves hydrodynamically. Also, it needs viscosity. A very small amount of viscosity is required to explain what we observe in the detectors. Okay. So from QGP phase to Hadron phase and then to freeze out. freeze out is when the hadron phase no longer interact and go to the detector. Okay, up to the whole dynamics can be explained by relativistic fluid dynamics, the equations of hydrodynamics. Okay, and there are typical time scales, proper time in along which this happens, but those are numbers. Okay, so there are interesting new observables which were found in heavy ion collision, and that actually led us to believe that there are signatures of, quantum mechanical signature in relativistic hydrodynamics. Okay, and this were spin polarization. Spin is defined quantum mechanically. If we talk about spin states, the fact that there are quantized spin state a direct consequence of quantum mechanics. Okay, so how do we detect that? How do we detect spin polarization in heavy ion collision? Okay, so let's consider a scalar particle, and let's consider decay of scalar particles. So if we have a scalar particle, then there is no spin to it. It's just a spherical ball. Okay, and if we want to study the decay of the scalar particle or any particle, the decay is best understood in the rest frame of the particle. So you go to the rest frame of the particle, then if the particle decays into, let's say, two daughter particles, then they will come back to back. To conserve momentum, they have to be emitted back to back. Okay, but in which direction are they emitted? If in case of scalar particles, it's random. So if, for example, in the rest frame of the particle, if it were to decay into two particles, then whether it will be emitted along this direction or this, the direction is completely random because there is no preferred direction. It's completely spherical. There is no preferred direction in the rest frame. So isotropic decay products is what we expect. What happens when there is decay of particles with spin? So roughly speaking, it will be like, a particle is spinning, like a ball is rotating about one of its diagonals. Diameter, yeah. And then it breaks apart, so it will have more tendency to throw the debris, the decay daughters along the equatorial plane because it's rotating. Yeah. So basically there is a preferred direction due to spin. If a particle with spin decays, then it has a preferred direction to be emitted. Okay. So there will be anisotropy of the decay products, and this is basis for polarization observables. Okay. So we study the decay and we see whether the decay particles are isotropic or not. Okay. So now, but we need particles with spin. We need particles with intrinsic spin to decay, and they will have effect of they will be useful for polarization observables. However, if the spins are randomly oriented, there are many spin-half particles, let's say, or spin particle, then averaging over random decays would again lead to isotropic decay products, because now there is in the orientation there is no preference. In the orientation of the spins, there is no preference. So if I average over, even though particles are with spin, but if we average over them, no anisotropy, still isotropic decay products. Okay. However, if they're spin polarized, if the orientation direction is preferred, there are more alignment of spins towards one direction than other direction, then again we will see anisotropy in the decay product. Okay, so this is what carries the information about whether the medium is spin polarized or not, because the fact that they are preferentially aligned, the spins are preferentially aligned along one direction, means the medium is spin polarized. Okay. And this was observed in decay of lambda hadrons, okay, in heavy ion collision. Okay. So on the y-axis, you see this percentage polarization, which carries the information about the anisotropy of the decay products, and x-axis is the collision energy, the energy at which you collide the nuclei, and you see that there is some anisotropy even beyond the error bar. There is some anisotropy of the decay products. Okay, and that leads to the claim that there is the first evidence of quantum effect in relativistic hydrodynamics. Okay, this was the spin polarization observable, and the explanation comes from the argument that there are large angular momentum, which I will talk about how angular momentum is generated in heavy collision, and basically it led to the claim that there is huge vorticity, subatomic swirls, okay, and most vertical fluid ever, and such claims. And indeed, you need very large vorticity to explain these polarization observables, okay. Spin polarization observables. There are other effects as well, which is related to spin polarization. So one of them is Einstein-de Haas effect. So let's see what that effect is. So if I take a ferromagnetic material, the blue object here, and I hang it with a thread, okay, and I keep it in magnetic field, the coil, when I switch on the current, will generate a magnetic field. Okay. Now ferromagnetic materials have electrons, almost gas of free electrons. Okay. So these electron spins in the presence of magnetic field electrons are charged particles. Okay. So spin of particles being charged has magnetic moments, very small magnetic moments. Electrons are magnetic, so they're like small magnets. Each of them are small magnet. Okay. So if you put a magnet in a magnetic field, they align themselves. So if the electrons will align themselves. So the spins will align. Okay. Spins being aligned means there is an unbalanced angular momentum now being generated. Spins behave like angular momentum. Okay. So spins being aligned will generate an unbalanced angular momentum, and the ferromagnetic material will have to rotate in the opposite direction to balance this angular momentum, because to begin with the ferromagnetic material was not spinning, not rotating about its axis. Okay, so you see that it spins, and then you observe it by shining a laser on the reflector, and then the laser changes the angle. The angle changes, and therefore this is how you observe that actually the ferromagnetic material rotates. Okay. So what did we do? We put a ferromagnetic material in a magnetic field, and it rotates. That's the cause and effect. Okay. So how about we rotate a ferromagnetic material? Will it generate magnetic field? And indeed, that was found that if you just take a ferromagnetic material and rotate it very fast, okay, so it generates magnetic field. Okay. The transformation of orbital angular momentum, this leads to spin alignment and therefore magnetic field. Okay. So magnetic field causes rotation of ferromagnetic material, and rotation of ferromagnetic material also causes magnetic field. Okay. This was the Barnett effect, the converse of Einstein-de Haas effect. Okay. So what about heavy ion collision? Do we see similar features? Right. So indeed this happens. So remember, nuclei are just they're not atoms, they're just nuclei, which is positively charged nuclei. They're moving with certain impact parameter. So basically charges moving with certain impact. So there's a current, there's a huge current, they're moving very fast. Okay. So there's huge current, and since there's an impact parameter, so there's this the radial separation between the two currents. Okay, and that generates a magnetic field. Okay, and this magnetic field is actually very, very large, 14 Tesla, which is, but very transient magnetic field. It lasts for a very short time, but still the highest magnetic field on Earth could be attributed to this, short-lived but very large, 14 Tesla. Okay, and it decays at the speed of light, almost at the speed of light, because the nuclei are moving at the speed of light. So once they move apart, then there won't be any magnetic field in the overlap zone. Okay, so these ones, the purple ones, are called spectators. So once they move apart, there won't be any more magnetic field in the overlap zone. Okay, so the blue dashed line is when you just calculate the magnetic field as a function of time, and if the medium has conductivity, the magnetic field lasts longer, which is the black and red solid line. Okay, the y-axis represents magnetic field measured in the units of m pi square, mass of pion squared. It's a standard units that we use to measure the magnetic field in heavy-ion collision. Okay. Similarly, we also have angular momentum, large angular momentum. So, because again, this nuclei, which are not uniform, they have like Wood fraction distribution. So they are moving at with some impact parameter, and the overlap zone will now rotate. So it's like two balls collide and they leave the collision, the part where they collide with some impact parameter. That part, if it is separated from the two balls, it will keep rotating. This is the angular momentum. The direction of the angular momentum magnetic field is along the same direction. Okay. So this is global angular momentum in heavy-ion collision. Okay, and you can see that you can calculate it using some simple models of Hart sphere for the nuclei or Wood fraction distribution, and the angular momentum in units of h bar. So J is, you see, there is no dimension because we measure that in units of h bar. H bar in natural units, we take them to be 1. So in units of h bar, it's around some tens of thousands of h bar. Okay. Compare that with nuclear spins, you find it like few h bars, like 10 by 2, 15 by 2 is towards the high end of the nuclear spins. Like nuclei with their spin is very small. This is very large spin of the fireball. Okay. Now our motivation, I come back to this slide again. So our motivation is the following. So we have huge magnetic field, we have angular momentum, okay, and we know that QGP has to behave hydrodynamically. So basically, we are talking about relativistic hydrodynamics, which should have angular momentum conservation and magnetic field taken into account. So hydrodynamics with magnetic field is called magnetohydrodynamics. Okay. So we have to formulate relativistic magnetohydrodynamics with angular momentum conservation. Okay, that is the challenge that we took to solve. So we have to formulate relativistic spin magnetohydrodynamics. The spin magnetohydrodynamics, the spin hydrodynamics is the one which has also angular momentum conservation inbuilt. Okay, and yeah, so and the idea is that you see there is this difference of lambda and anti-lambda polarization. Okay. So if it was just angular momentum, then you would not see any difference of lambda and anti-lambda polarization. They would be the same. But the fact that they are not the same means there is a magnetic field effect at low energies. Okay, at low energy there is a magnetic field effect, and therefore there is a difference of lambda and anti-lambda polarization. Okay. So so what is angular momentum conservation? So let's talk about angular momentum conservation for particles. For particles, the angular momentum is defined like x cross p. So you can then write down the components of the angular momentum using the Levi-Civita. The cross product can be written like this, and this is the component of the angular momentum L. One can, in turn, using this L, calculate the dual of the vector. Okay, this is an antisymmetric tensor in I and J. Okay, and they have the same degrees of freedom. Lij and Lk would each have 3 independent components. Okay, and you can write them in terms of x and p like this. We know that both equivalent. Both definitions are equivalent. Lij and Li, both these definitions are the same. Okay, just different way of writing them. Okay, and then we also have conservation of angular momentum. If there is no torque, then this has to be fulfilled. And from this definition, we also have this del I is del xi. If I take a derivative with respect to x on both sides, yeah, we'll get this to be 0. Okay. Now, relativistic generalization. If I for a point particle, if I were to generalize this to relativistically, all I need to do is change ij to mu nu. This is what we have, and this will be fulfilled. Mu and nu goes from 0 to 3, and ij goes from 1 to 3. Okay. This treatment is valid for point particles. For fluids, what we need to do is we need to replace the particle momentum with generalized fluid momentum, and the generalized fluid momentum is the energy momentum tensor. Yeah? So, which we saw that earlier, that the fluid momentum, energy for momentum would be the energy momentum tensor. The same definition that we had for point particle, we carry to fluids. Only thing is that the P is replaced by T. Okay, and it's the same definition. And keeping in mind that we have energy momentum conservation, which is energy momentum conservation is written like this: the conservation of energy momentum tensor is 0. Okay. The 4 divergence of T mu nu is 0. Then using this, we see that the divergence of orbital angular momentum, this is orbital part of angular momentum for a fluid, okay, is equal to the antisymmetric part of T mu nu. Okay. Now this is interesting. So T mu nu is energy momentum tensor, and classically T mu nu is always symmetric. So in the sense that T mu nu has to couple to Einstein gravity, and Einstein gravity G, the metric is symmetric, and so on. So that is symmetric. So therefore, orbital angular momentum is automatically conserved if we have symmetric energy momentum tensor. Okay. However, because orbital part is always conserved, the previous formulation of relativistic hydrodynamics did not bother about angular momentum conservation. Okay, but the problem is not so simple when we have also intrinsic spin of the particles. So the total angular momentum has to be conserved, not just the orbital part. And the total angular momentum is orbital plus spin. And we have to ensure the total angular momentum conservation. And this is what is the basis for formulation for spin hydrodynamics. Okay, the hydrodynamics is the angular momentum conservation. Okay, so this is going to be a little bit technical. So total angular momentum can be written as orbital plus spin, and we have energy momentum conservation, and orbital part follows this equation. Then total angular momentum conservation implies that the spin has to have this relation, the spin part of the angular momentum. Okay, so these are the equations which should be fulfilled by a relativistic hydrodynamic system. Okay, this should be the ones which should govern the evolution of relativistic hydrodynamic system. Okay. However, we see that there is a problem now. These two quantities are not uniquely defined, in the sense that we know that there are these dynamical equations, but there is a freedom of phi. If I make some certain redefinition of S and T by S tilde and T tilde, still the tilde quantities follow this blue equations. So I can just replace T tilde, S tilde here, and we still have the same equation of motion. So there seems to be freedom, and this freedom is actually due to this is like a gauge symmetry, gauge freedom. We call this pseudo gauge transformation. Okay, and this is due to the fact that we have inherently assumed that we work with Riemannian geometry, and therefore we don't have torsion in the space-time, and including torsion actually fixes this problem. And one of the topics that we're interested in is how to fix this freedom. I will come back to it at some point. Okay, so our formulation within kinetic theory. So what we did was we worked on this this problem of relativistic spin hydrodynamics and spin magnetohydrodynamics within kinetic theory. So what is relativistic kinetic theory? So relativistic kinetic theory is working with distribution functions, which gives me this quantity F, which is the distribution of particles, times a small phase space volume element, gives me the number of particles in delta 3x, the spatial volume, which is located at point x, which has particle in momentum range P and P plus dP, okay, P plus delta P. Okay, this is what this gives the number of particles. Okay, and the energy relativistic is only this relation for energy and momentum. P0 is energy and P vector is momentum, and that's the only relativistic information that goes into our relativistic kinetic theory. And of course, for statistical or kinetic theory description, we have to have this statistical assumption that number of particles in this delta 3x volume has to be large, so that you can make averages. You can define temperature and energy density, and so it has to be large. However, this small volume has to be small compared to the full macroscopic volume, the full fluid. This small volume where we make, we take local volumes. This local volume has to be small. There's a question. Sorry. Okay, I'll continue. Yeah. Okay. So the distribution, equilibrium distribution function is given by this 1 by exponential of E by T minus mu by T. The xi is mu by T. Beta is sort of 1 by T. In here, it will be a little bit, the definition will be a little bit more involved. We will have a relativistic 4 dot here. Beta is u mu by T, a certain time-like vector, unit vector, and P is the 4 vector, the 4 momentum vector of particles. In the small volume, but that small volume is small compared to the total volume, macroscopic volume. Okay, and this is the usual form we get for plus for Fermi-Dirac and minus for Bose-Einstein statistics. For the distribution function, beta is like 1 by T, P will be like the energy in certain frame. Xi is the ratio of chemical potential and temperature. So what happens is, for non-dissipative system for particles with spin, we have extended phase space. Okay, so S is the in the sense that now the phase space is not just composed of space and spatial part and momentum part, but also the spin part. Okay, so the distribution function has this extra contribution in equilibrium, which is because of spin. Okay. Remember, we have kinetic theory, so that means we have this is still a classical description. Okay, so with all that, we can still define the equilibrium distribution function, and what we get is, with this distribution function, if we can have the definition of the conserved currents, and that gives us ideal or non-dissipative spin hydrodynamics. For dissipative spin hydrodynamics, we have to calculate F out of equilibrium, and we use Boltzmann equation for this, how to obtain F out of equilibrium. Once we have that, we put it here, and we have our definitions of the conserved or expression of conserved currents. One thing to notice is that we have to have a classical analog of spin, because now the phase space is extended, so this phase space is supposed to be continuous up, and because of that, we have the way we classicalize spin is that we define a sphere with this Casimir factor, that is the radius of the sphere, the spin sphere, and say that instead of this plus half and minus half, which is the quantized state for spin half particles, all points on the sphere is probable, equally probable, and therefore we have to integrate over spin. That is the classical treatment of spin. Okay. With that, we get dissipative spin hydro. So what are the dissipative effects? So we know that like shear viscosity leads to fluid's resistance to shear forces. So between the resistance between layers, motion of layers, that is shear viscosity. Similarly, we have bulk viscosity, which is resistance to compression or expansion. We can also define conductivities, charge or heat conductivity, okay, which leads to flow of charge or heat between two, for example, heat current flows between two different temperatures. Okay, but there is something new which comes up, which is the dissipation in spin current. Okay, so this S lambda mu which we define, this is a new current which we have, new conserved current, and that also has dissipation. Okay, so one can also include magnetic field, so effect of electromagnetic field essentially. Okay, so we have the fluid part of the energy moment tensor, we have the electromagnetic field part of the tensor, and we have the fluid field interaction. All that affects the energy momentum tensor, and basically one can combine all that together into spin magnetohydrodynamics. This is our recent work in this direction. What additionally we observe is this effect of Einstein-de Haas and Barnett. These two effects we can describe within our formalism. So the equilibrium magnetization tensor can be written in terms of the distribution function. And when we integrate over the spin and the momentum, particle momentum, this is what we have. The magnetization is proportional to omega. This omega is the Lagrange multiplier. Okay, so this work was done in collaboration with my student Samapan Bhaduri and other collaborators. It was his PhD thesis work. He is now postdoc in Poland. So he mainly worked on this dissipative spin hydro and relativistic spin magnetohydro. The ideal part we have been developing earlier, the formalism of ideal spin hydrodynamics. Okay, so he included dissipation and magnetic field in the earlier formalism. And in our work from geometrical approach, we are trying to understand, given a Lagrangian of a theory and the symmetries of the Lagrangian, how can one construct the Noether's current? So, for example, energy momentum tensor is, and conservation of energy momentum tensor is artifact of the fact, or rather symmetry, due to the symmetry that there is a diffeomorphism invariance. So volume preserving diffeomorphism invariance, which means that a change in metric or change in space time will the Lagrangian remains invariant. This is energy momentum conservation. Similarly, current conservation is due to gauge symmetry. So spin current we can also similarly construct, but for that we have to we have to consider non-Riemannian geometry, and the spin current comes because of the variation with respect to torsion. Okay, so that is what leads to angular momentum conservation, which is essentially a consequence of local Lorentz invariance. Okay, and so with Saurav, one of my other students, I'm working on these aspects and also trying to formulate Kubo relations for spin current. And then there have been several other works in this direction by Frankfurt group from Wigner function approach, and also approach from kinetic theory by the McGill group. And there is a Brazilian group who are working on Lagrangian method to such a similar formalism of spin hydrodynamics. And the string theory people, or the gravity side, people from gravity are also interested in formulation with torsion in the metric. Okay, so there are a lot of groups who are interested in this, and one can find useful reviews on spin hydro in these articles. So relativistic spin magnetohydrodynamics is actually a completely unexplored area. I mean, our work are first. Thank you.
Thank you so much, sir. You give us such a theoretical development to understand our laws of nature and through spin hydrodynamics like this. For such an enlightening and interesting topic it is. And I think is there any questions in the chat box? I can check once. Okay, so thank you so much. Okay, one question is there from Dr. Radhakanta sir. The question is the ion intensity uniform in the QCP, or perturbation of ion intensity?
Deepika, your voice is breaking. Can you repeat the perturbation of ion intensity? Heavy ion. Let me go.
I am reading the question.
Yes.
Is the ion intensity uniform in the gap, or perturbation of ion intensity is considered? This is the question.
Ion intensity. Okay, so here for heavy ion collisions, okay, we are actually talking about single collisions. So of course there are a bunch of ions which are collided, but when we talk about QGP, then it's only one single collision. So in one single collision, the intensity of ions does not really matter in that sense. One single collision of two ions, two, let's say, lead or gold ions, that is where, so basically these events are well separated in space-time. So what we observe are happening at femtometer level, and the densities or intensity of ions are at micrometer or I mean, they're not of the femtometer scale, so they're very well separated in space time. So they don't really affect the QCD evolution, the ion intensity. Was it clear?
That means statistical is neglected.
Yeah, well, I mean, they don't really affect the evolution of QCD. So that's
what Sarah's asked. That means statistical distribution, is it neglected?
Statistical distribution of ions in the heavy ion collision?
Yes, sir.
Okay. So in that sense, they don't, I mean, yeah, they are not, they don't really affect. There are huge separation of space-time between what is happening in one collision and what is happening in other collisions. So in that sense, yeah, it's neglected. Yes.
Okay, thank you, sir. Sir, one question from my side. So, if we know that our space is curvilinear, I mean it is curved space, then is it is there any necessary to do those things in flat space, or the result is more useful in curved space to formulate?
So the idea is the following: what is happening on Earth is actually, the gravitation due to Earth is weak field. So when we can actually consider weak field approximation, and we can actually neglect Earth gravity. So it will not really have, on a very small scale, it will not really affect the heavy ion collision. It is the strong interactions will not be affected by gravitational pull of Earth. So what we are having, the experiments on Earth are not going to affect it. However, why am I talking about torsion in the metric? Yeah. So let's going back to that question. Actually, torsion is something which is only required to generate the current. So it's very similar to your QFT calculations, where what we do is we introduce currents. The currents are the ones which generates the 2-point or n-point functions. So derivative with respect to current we take of the Lagrangian, and they generate the 2-point function or n-point function. Later, once we have taken the derivative with respect to current, we let the current go to 0. Okay, and we get the endpoint functions. Okay, that is very similar to how what we do is we introduce torsion in the metric. We take derivative with respect to metric, which generates the spin current, and then we let torsion go to 0, and we still have a non-trivial result. So we don't really keep torsion in the metric. We don't really keep torsion in the space-time. You understand?
After all, we have to lead it to 0. I mean, torsion geometric to.
So we don't really
thank you, sir.
Put up the geometry, but it's a way of creating the currents, the conserved currents that we are interested in.
Okay. So another question from Swaraj Patnaik: is the study of magnetohydrodynamics is helpful in fusion energy production field like fusion reactors?
Right. So magnetohydrodynamics is actually very important in solar physics. So this, if I want to understand what happens in sun, it's basically completely, controlled by magnetohydrodynamics, non-relativistic, but still magnetohydrodynamics. And that's one well-known source of fusion. That is one big fusion reactor that we have here, not here on Earth, but in our solar system. So sun, the dynamics of sun is indeed governed by magnetohydrodynamics. So in that sense, magnetohydrodynamics is important for fusion, nuclear fusion studies.
Okay, one more question. Thank you, sir. One more question is there also. How does the initial space anisotropy get converted to final momentum anisotropy?
Yes, good question. Okay.
Does it satisfy the conservation rule?
Yes. So it is more like imagine this green zone. Okay. So imagine you have a balloon, for example. Okay. You take a balloon and which is spherical, filled with air or water. In this case would be even better. So fill it with water, and then you compress it along one of the directions, so that it looks this shape of this green shape. This elliptical shape. Okay. Once you release it, so you keep it on the table and then you release it, you see that there will be faster expansion of the balloon along the direction in which you compressed it. Okay. So what it tells me is that you put up, so inside the water there is same pressure. Okay. But the pressure goes from P0, which is inside the balloon, to 0 quickly along x-axis, along the direction in which you compressed, compared to along y-axis. So once you release it, this pressure will try to push the balloon more vigorously towards x-axis. Now imagine this is what happens in QGP. The only thing is the shape is there is no surface tension, so it's not exactly the same thing as balloon, but this shape is formed in vacuum with a smaller extent along x direction than along y, and then the QGP expands. It will expand faster along x than along y, so it will throw more particles along. So if it is expanding, then there will be more chances of particles coming along px, along x, than along y. Okay, and therefore we see this elliptic anisotropy in the momentum space. There is more particle along x compared to that along y, and which is because of the fact that initially the spatial anisotropy was opposite. Okay, and indeed it conserves and everything because you apply hydrodynamic equations. Hydrodynamic equations are just the conservation equations, so we don't really violate energy, momentum, or current conservation. So therefore, everything is conserved. But yeah, these particles that we observe, what is coming out, could be more biased towards x-axis because the pressure were biased along x-axis initially. Was it clear?
Yes, sir. Thank you so much. So there is no more questions. Once again, on behalf of OUTR, I would like to convey many thanks to Professor Amresh sir for his valuable contribution in this webinar. Thank you so much, sir.
Thank you.
And,
Thank you, sir. Thank you very much, sir, for the nice presentation you delivered. Thank you,
madam. Thank you for inviting me. I really enjoyed. I would at some point like to really come and visit the university.
Yes.
Yeah.
I also want to invite you to visit our university and interact with a student in the physical mode. That is more interesting.
Yes. So maybe in early next year would be nice. Yeah.
Yes. Yes,
yeah.
Yes, sir. I will invite you.
Okay.
And thank you for joining us.
Thank you very much. Bye.
Now I request Akash sir to give vote of thanks.
Good afternoon, everyone. I deem it a great honor to propose the vote of thanks to everyone who helped us to ensure the resounding success of this faculty development program, a webinar on quantum transition from ions to cosmos. First of all, I would like to express our profound gratitude to Honorable Professor P.K. Patra, OST OUTR, Professor N. Acharya, PCM Coordinator, Professor P.K. Satpathy, PIC Academic PG, Professor L.N. Tripathy, PIC Academic UG, for their valuable time, support, and encouragement for organizing this event. The event would not have been in this shape without the consistent effort and guidance from our beloved head of the department, Professor Babita Ojha. Ma'am, personally, I must say, words are not enough to acknowledge your contribution throughout. I must extend our hearty vote of thanks to our chief guest, Professor Naresh Chandra Mishra, sir, who graced us with his thought-provoking address and set a perfect platform for our faculty development program. I would also like to thank all the distinguished speakers from India and abroad who, despite the busy schedule, have made their calendar free for us. Their fact-enriched excellent presentation, mind-boggling interaction session have indeed made the webinar exciting and meaningful. The success of any event is always measured from the involvement of the participants. We are thankful to have such nice audience. We have received a couple of suggestions to extend the interaction time and also to conduct these interesting talks offline. I must say, on behalf of the organizing committee, we are up and coming. No event can happen overnight. To make this possible, several members have spent hours to make everything in order. I'm happy to express vote of thanks to our moderators for the sessions, Dr. Samita Patnaik, Dr. Prachi Mohanty, Dr. Barsa Purohit, Dr. Sapurja Samarpita, and Dr. Deepika Das. This virtual event would not have been possible without necessary technical support and arrangements. A special thanks to Dr. Rakesh Ranjan Sahu for looking into the technicalities of the event. Last but not the least, we must also like to express our appreciation to the class representatives of all the batches for looking over the coordination and necessary arrangements. A special thanks to Mr. Mishra, class representative 3rd semester MSc, for his round-the-clock presence to handle the errands. Finally, the wonderful students who have turned up in such great numbers. Thank you so much for your cooperation. Once again, we would like to convey our sincere thanks to all for your cordial cooperation. Thank you.